Starting preview. I'm waiting to see if we're going to see me. I'm just waiting. Tick tock, tick tock. Thank you all for joining me today. I appreciate it. And I'm hoping people are going to see me soon. If you see me, say yes. Give me a thumbs up in the chat or give me a big hello. I think I'm seeing myself now. So give me a thumbs up. It looks like everything is running okay. And I'm hoping everybody's enjoying themselves, despite the fact that we're probably all sequestered in our homes and just hunkering down, hoping that we can get through all this craziness. Everybody's staying well. I know a few friends of mine who are suffering, from the bug. And thus far, everybody's okay. But, this isn't fun for any of us. So hopefully this will give you a little bit of, she survived, yes, yes, coronavirus free thus far. Hopefully this gives us a little bit of levity and normalcy and just distraction from all of this worldwide nutsy stuff that's going on right now. And the funny thing, if you want to hear a little joke, I'm so used to teaching at Millersville University now, and I do it through Zoom. So, and I've been on Zoom so much with everything that's going on. Because I'm getting my husband's business online, and my daughter is now learning on Zoom. I mean, she's in 4th grade, but she's learning on Zoom. So everybody's on Zoom. So I immediately, for this class, put in my earpiece, and I'm all wiring it up, and I'm getting frustrated because it's taking so much time because I'm trying to untangle the cords. You know how cables get always messed up, and then I realized I was halfway done, and I went, wait a minute. Who am I listening to? They're going to be chatting with me on the screen. I don't need to do it for this. So, all of us are trying to adjust to this whole new world that we're living in. So, anyway, yes, I hope everybody simply, oh yes, I see that. Thank you. My prayers for your friends affected. I appreciate it. I hope everybody is staying well. Yes, I see Steve, you're from Zurich, and I hope I was in Zurich not that long ago. That in Bern, Switzerland, and it's a beautiful country, and I know you're being pretty seriously affected by this virus. So everybody stay well and stay safe. So, and yes, I see people from Scotland. Thank you so much. Just get on with it and stop worrying. I can't help it. I'm a woman. I worry about everybody. It's just what we do. We're wired that way. So, all right, enough of that. You're right. Let's get going. Okay. So this is, if you are here, hopefully you have already watched the previous course, because this is a follow-on from the course that we did before. This is the second of probably, I would think, 3 courses that we're going to end up doing. I'm going to get into the next course will end up likely being about cosmic rays and how they kind of fit into this whole story of radiation storms. They're a slightly different, well, a very different kind, depending upon your point of view. There's a lot of similarities, but there's a lot of differences as well. So we will get into that most likely next time. So if you wanted to get into cosmic rays, you got to wait one more class. But this one is going to be continuing the discussion that we had of solar radiation storms. I will review just a little bit of what happened last time. And for those of you who stuck around to the very end, you got to see some really cool stuff. I will go over some of that again. And then we will move into how these radiation storms, how they impact Earth. And I will show you some examples of how big they can get. They're really some of the most intense aspects of space weather. So it's and they're likely the most biologically active as well. They're definitely the hardest thing that we need to overcome when it comes to things like Mars and the Moon colonization. The radiation storm problem, don't let anybody fool you. It has not been solved, and it is going to bite us in the behind for quite a few more years before we figure out how effectively to protect the softest parts, so to speak, which are the biology, the human itself. We can send up satellites into space, and we can harden them, make them what we call radiation hard, but you can't do that to a human body. So it's very, very difficult for us to do this effectively, and you'll see some of that today. I'm just looking to see if there's, everybody can hear me okay? My audio isn't too quiet, it isn't too loud, no distortion. I just want to make sure everything's good before we go. I'm making sure none of my VIPs are texting me telling me something's wrong. Jerry, uh-oh. Yes. Hi, Jerry. I am monitoring today. Thank you. I'm going to text him back and say, thanks, Jerry. Actually, he's probably, why am I doing that? He probably knows that. So I don't need to do that because you just are watching. And I also have some Patreon people that have already said they're watching. So thank you, Mike. Thank you, Notani and Andreas. Thank you so much. I see you guys on Patreon. So don't be shy about putting questions on Patreon if you'd like, or also just do it here in the chat. I am watching. Okay. So everything's good. 10 by 10, 5 by 5. Awesome. Thanks, guys. So I will go ahead and get started, and well, let me first, as I always do, let's see if I stand on the right side here. Yes. Let me first thank my VIP committee. I have not added everybody in here yet. This has not been updated as of April. So this is still my March group, and we have a few new people who've come online, and I'm loving it so far. Stacy, Nikki, for example, you guys are new. Bernie, I'm so great to see you actually in the VIP meetings now. I hope that'll be a new trend, and we'll get more and more people. Also, the mini course patrons. Again, I have a few people that need to be updated here, so if you don't see your name here this time, you will see it by next month for the next mini course. All of you are making all this happen. I mean, I would not be able to do any of this without you. So thank you so much for all of your generosity and for the family and for the input and everything else to make not just these courses happen, but actually steer the ship and get space weather broadcasting and space weather communication online is a real viable field, you know. You're not just helping, you know, non-experts in the field. You're helping meteorologists who want to get space weather chops, and you're also helping, believe it or not, you're helping space weather experts who are experts in one small arena. Like you have ionospheric experts, or you have solar experts, or you have magnetospheric experts, and they don't have the well-rounded, you know, knowledge of this entire field. And I have actually had a lot of those people contact me and say, hey, Tamitha, you know, I watch your courses and I've learned so much about the other aspects that I don't really touch on. And so these are PhDs in the field. And what's nice is that you all are helping them get a more well-rounded appreciation of how space weather affects everything. And, you know, basically from sun to mud. Whereas a lot of these people would stay in their own little niche, you know, in their own little discipline and really not step outside of it. So I think it's really overall, as time goes on, you're really helping so many different people learn more about space weather, and I'm just so internally grateful. So okay, so let's start. This chart, I always begin with this chart so that you guys can really take a look and remind yourselves that when it comes to Earth, there really are basically four types of phenomena that we really worry about. Okay, now we've already done solar flares. That's this guy over here, and I probably don't have to play the movie, but I will if anybody screams at me and says play it. But there's a solar flare right there. It's like an X2 flare. We also have solar storms, and these are also called coronal mass ejections. I've done a bunch of courses on these as well. Okay, and now we're getting down to solar radiation storms. Okay, the one I'm hiding behind me are coronal holes. These are fast solar wind coming from these big dark coronal holes that you see. No, they're not really holes on the sun. They're just cold. It's just colder plasma, colder. The sun's atmosphere in this region is colder, and so it's dark because it's not emitting light in this particular wavelength. So it's not really a hole. You can't fly through it. The sun's not cracking in half. But from this region comes fast solar wind. Now, believe it or not, all three of these phenomena, okay, drive solar radiation storms, which is, whoops, over here. Okay, so we get solar radiation storms from all of these three types of phenomena. And this is one of the reasons why I started teaching the radiation storms after I had already gone over what these things are. So if you have not had a chance to take a look and see what solar flares are all about, or see what solar storms are all about, please go review those, you know, at your leisure, obviously. Those mini courses. We have probably, oh my gosh, something close to 10 of them now, because I keep doing it in bits and pieces so that we can get a really intense and a really in-depth view of what solar radiation, or what all these phenomena are. And I will go into, kind of where we left off, I will go into the two class, scheme that we believe our solar radiation storms. Whoops, on this side, solar radiation storms are driven by. And I started talking about that last time, and I'll go review that. But here is what solar radiation storms look like. If I make sure I stand on the right side. So here is a coronagraph, if anybody is familiar with this. The coronagraph, this is what we often look at solar storms coming off of. That's what you're seeing, those big white puffs. Those are solar storms being launched, and oftentimes there's solar flares in there too. But you're seeing a big solar wind all blowing off of the sun there. And this is kind of like a false eclipse. But you'll see a solar radiation storm. Well, there's a small one right there, and you'll see a big one in just a moment. This was the Halloween storms. There you go. Look at that blizzard. Bam, right? And you'll see more of them. Let me just stop it right there. Okay. These solar radiation storms are driven both by solar flares and solar storms. And what you're seeing is the intensity of these particles actually hitting the detectors on this coronagraph. This coronagraph was designed to detect Thomson scattering by electrons. It's looking at light. And when the CCD get hit by these really energetic particles, it actually causes traces. They actually deposit energy, and it comes up as a detection. You know, it's changing its voltage, it's changing its bias, it's giving it a signal. And so these streaks that you're seeing is actually the particles going right through the detector at different angles. That's why you get these things in all different directions, because the particles are coming in from all sorts of angles, because the particles are spiraling along a magnetic field. So as they spiral in, you know, sometimes they'll hit it this way, sometimes they'll hit it that way. So it causes all these different streaks. The interesting thing, of course, is that this is analogous to what astronauts see. Okay? When there's a solar radiation storm, if they're not in a protected place, they close their eyes and they see very similar things. Some of them have described it as fireworks in their eyes. And they see it even from cosmic rays, which we'll get into in the next course. But these solar radiation storms, there's energetic particles that are relativistic, and they're so energetic that they can actually pass right through you. Okay, now again, as a review, remember this from last time. Okay, solar storms and solar flares cause radiation storms. So we have coronal mass ejections. This is on this side, and if I play this, I probably have this up as a movie. Yes, I do. So I'll go ahead and play this for those of you to remind you. I know you've seen this movie over and over again, but here you go again. There it is coming off of the sun. Right there, and you'll see it blow out into the corona. Whoops, sorry, I'm pointing in the wrong place. You'll see it begin to blow off into the coronagraph, similar to what we've seen. See it blow off like that. It's still kind of a big loop coming out into the sky. And these coronal mass ejections, these big solar storms, I'll freeze this here, drive big shock waves in front of them. And because of that, they actually will cause solar radiation. Those shock waves will actually drive those solar radiation storms, and I believe I talked a bit about that last time. The shocks will accelerate particles even further, so if you get a seed population from, let's say, a solar flare, if you have a solar storm that's launched along with it, that shock will then drive those particles to even higher energies. So as you'll see in the two-class picture, the solar flare can create a seed population of very energetic particles. But in order for that seed population to last and continue to get energized over and over and over, you need a solar storm. Okay? And that becomes two totally different mechanisms that are accelerating these particles and making them be relativistic and be what we consider a radiation storm. Okay, so right now it's still a very hot topic to try to figure out how fast these particles can get. There's something called the streaming limit. Anybody who's interested in that can look up several papers by Hillary and Kane, by Don Reams. You can just look up streaming limit and see how shocks can get particles past that streaming limit. We really don't know to what energies these particles can be accelerated to, but we have seen ions be accelerated above 1 GeV, and that's incredibly energetic. As a matter of fact, it's so energetic that this kind of energy means that solar energetic particles can actually cause cosmic ray showers and be detected on the ground by neutron monitors. And we'll talk about that in the next class. Now, solar flares, these guys are faster. They release a shorter burst of energy, and they can also accelerate particles up to very high energies, but they don't necessarily, they're not driving that radiation storm all the way to Earth. So when you see these types of events, they often are called impulsive events as opposed to gradual events. Remember, all of this should be review from last course. And so if you only have a solar flare, the radiation storm that's associated with it, if a radiation storm is launched, it's most likely going to be shorter. Okay, and we'll talk a bit more about that. And let's see, do I really want to go over this again? This is really to remind those who recall the standard model of solar flares and coronal mass ejections that basically what I didn't talk about in those courses, right up here where we talk about this X line, this area where all the what we call the reconnection is happening. You've got stuff coming back to the surface that's below that X line. You've got stuff lifting off, that becomes the CME that's lifting off above that X line. But what also is lifting off are, see how it says electrons? You also have protons, electrons. This is where the energetic particles come from, and they also can come from the sides of this. Okay, that's part of the seed population. And then as these particles move out along with that big solar storm, the shock wave in front begins to accelerate them even further. Okay, so really when you have these particles being released, they can be released typically not so much in the precursor phase, but definitely in the impulsive phase, which is in this side, which is the reddish region, which is kind of like what you're seeing right here in this diagram behind me. The impulsive phase where everything is changing, the magnetic field is reconfiguring. But then also it continues out through the blue here, which is that gradual phase. That is where the big CME, the big solar storm, is continuing to launch and leave. So you still get acceleration of particles all the way through that region. So the difference between, let's say, an impulsive flare-driven radiation storm is that you get a shorter burst. If you add a coronal mass ejection in there, you're going to get a much larger, even just by looking at this, you're going to get a much larger and longer duration radiation storm, but even longer than you'd think just from this diagram, because that radiation storm is actually going to continue all the way until that shock wave from that big coronal mass ejection passes you. So that big solar storm is driving the shock wave in front of it. That shock wave is accelerating particles, and as long as you see that shock wave, you're going to get particles coming from it. It's going to be, coming at you like a big freight train. So that means that even though a solar flare hits and is over with in a few hours, maybe even less than an hour, right? Everything dies down. It ain't over. The story ain't over. If you've got a big solar storm coming at you, however long it takes for that big solar storm to reach you, 2, 3, 4 days, probably more like 3, because if it's 4 days, it may be slowing down so much that shock wave dies. And if that shock wave dies, then it's not driving particles nearly as strongly as it used to. But as long as you have a shock wave in front of it, meaning that is a pretty fast solar storm coming at you, you're going to be getting that radiation storm. So something that would normally last just a couple hours, and then die down, now could last a couple days or more. Okay, and we'll see that in just a second. I probably don't need to go over this too much. This is once again review. Hopefully everybody remembers this. This is just the standard model. I've used this. You guys should be completely sick of this diagram by now. Again, it's just another view of the loops in a flare. Let me come back over here. The loops in a flare. Everything below that X line, that's this region here, goes down. Everything above it goes up. And you can see the magnetic field in blue kind of threading through this structure. Looks kind of like a blue little ribbon kind of going through that. In this picture, they're just showing more, they're focusing more on the yellow is now that coronal mass ejection that's being launched. And here, as you can see, there's particles that are trapped inside the CME, but you can see all the little things here they're showing. These are like particles. If you go to this diagram, you can actually see they show trapped particles. But that is a source in this region. Whoops. Come on over here. This is a source region over here for particles all wrapping around this CME as it begins to lift off. But also, as you can see, the open field, if I can go here, see all this open field that goes up and out like this? Okay, you see there's energetic particles here too. So it's not just the closed structure that is this big coronal mass ejection, this big solar storm that's launching. It's also some of the open field around it where you've got particles that are escaping. Okay, so it's a much wider berth that can cause these seed particles to escape. And what am I doing here? And then as that CME begins to move further out into space, we also have to remember, last time we talked about the Parker spiral. Remember the Parker spiral comes around in an Archimedean spiral if you're looking down at the sun from the north. So if you're looking down on the North Pole, and as that big coronal mass ejection comes out, that big solar storm comes out, that big solar slinky, you've got, and I might as well just pull out my cute little slinky again, and it'll probably disappear as I put it in front of this thing, right? Yeah, it does. But if I try to, show you the slinky, right? That's this big yellow thing. I'm trying to kind of overlay the slinky onto this so you can see it better. It's disappearing, ha ha ha, oh well. But that's the slinky, okay, that's coming out, and it's attached to the sun at both ends, as you can see, up here somewhere. Come on. There we go. It's attached to the sun at both ends here where the blue is coming out. You've got particles that are streaming back and forth inside this structure, okay? But you also have that Parker spiral field that's coming out this way, okay? And you have particles coming out on those open field lines as well, okay? And really why I wanted to talk about that, why that's important to keep this picture in mind is for two reasons. First, you have that beautiful Parker spiral with all these spiral arms coming out. And you'd think, okay, well, how does a CME, how does a big solar storm move through it? Does it break the lines? Does it bend the lines? What does it do? Well, it kind of pushes them out of the way. It kind of, as it continues to expand out, the magnetic field lines can't really cross each other. It's like, just like when you hold two magnets together, they don't like to touch, right? So they push each other away and repel each other. That's kind of what's happening here. So as the CME continues to blow out, it's taking those Parker spiral arms and distorting them. Okay, it'll bend them out of the way, it'll do whatever it needs to do, it'll compress them, right? So when you're looking at this particular diagram, you see this black line, this is the shock wave that comes around, all the way around here. But then you see these Parker spiral arms from this, whoops, get my arm in the right place. The Parker spiral arm, field lines coming this way. Don't worry about the arrows. The arrows are pointing, they're just the magnetic field direction. Particles don't care about the field direction. That just changes how if they gyrate clockwise or counterclockwise, they don't care about that. What they care about is that those field lines guide their trajectory, guide their motion, like cars on a track to a great degree. And so as long as you see those lines, the particles are going to be following those lines to a great degree, irrespective of the direction of the magnetic field. So the particles are coming out from the sun. They're going to continue to come out from the sun, but they're going to follow all of this stuff, all these Parker spiral field lines, all the way down and in through the shock. And look where I'm at. I'm at Earth, right? So isn't it interesting that what ends up happening is that you have, let's say if you had energetic particles coming from this side, okay, coming from this side of the sun, you could actually get them to reach Earth, actually very quickly. You notice that's actually what we call a connectivity. Gosh, I'm noticing my green screen is failing me. I had it set really nicely. I don't know what happened. But so if you have a solar flare that's launching and that's firing off to the west from where you're looking at Earth, firing off to the west, you're going to have a better connection. You're going to have a better chance of getting these particles to hit Earth than if you did, even if maybe the solar flare was firing straight down from the sun, straight down the Earth-Sun line to Earth, simply because of the way that Parker spiral is. See that? And of course, if you had it off to the east over here, I keep pointing too high. If you had it off to the east, well, those Parker spiral field lines are firing off this way. So if you had energetic particles on the east limb, they're going to go off this way. What are the chances of them hitting Earth? Right? Not very well. So it gives you a hint that, hey, maybe if you're looking at the sun, you should be able to see which side of the sun is the flare is happening. And if the flare is happening on the west side of the sun, there's a much better chance of a radiation storm hitting Earth than if the flare occurs on the east side of the sun, right? Anybody who's ever looked at the Space Weather Prediction Center website and looked at what their predictions are for a radiation storm during, let's say, near solar max, or just when there's more bad actors, more bad, angry sunspots on the sun, and they have a bigger chance for big flares. If you ever watch how their predictions change, you'll notice that when a angry sunspot is on the sun and it's on the east side, the chances for a radiation storm still remain low. But as that sunspot continues to rotate and it gets to central meridian, meaning the Earth-Sun line, you start noticing that the radiation storm chances start going up. And then as you go to the west limb, radiation storm chances get to be big. And the reason why is because even if the sun, that particular sunspot fires off a huge X flare, when it's over here, there is a chance you won't see it at all at Earth. But if it fires off an X flare over here, oh yeah, you're going to get it. You're going to get it and then some. You're going to get it fast, simply because the connectivity with this Parker spiral is so good. Now, granted, there are violations of that, and I will show a few. But as a general rule of thumb, that is the way we see it. Any questions on that, guys? Before we move on, am I reviewing too much, or are we good? I'm hoping that people are happy with this thus far, because I'm beginning to get into the two-class flare stuff again. Looks like everybody seems to be pretty happy thus far. Okay, so the old picture, if I move on here, does it energize other planets? Yes, it does. The same kind of rules apply. I mean, the sun is the sun, and it doesn't matter what planet you are. You will see radiation storms. Now, granted, their intensity may die down a little bit as you move further out, because the density is just, it's dropping. You're going out into a larger amount of space, but you will still get radiation storms. Yes, we're good. No, we're good. Okay, good. You guys are loving it. Excellent. Okay. Tickle me and I'll hurt you. I love it. Okay. You're on 40 meters checking the propagation as it is happening now. I hope it's okay. We should have a decent, because we do have that new sunspot, and it is a solar cycle 25 sunspot. It's not doing all that much, but it is staying on as a sunspot right now. I don't know if anybody's checked the weather lately, but this new cycle sunspot is hanging on, and it's still visible, even in white light. So this is good. This is one of the longest lingering sunspots we've seen in the northern hemisphere for quite some time, and it's really good. A really good sign. Let's see. Is the video flipped? Are you pointing east on the right? Oh, okay. For those of you who have not, and I'm trying to remember, I think when I did the Millersville course, I put a compass rose on the diagram, and I don't think I did that for the Patreon version. So for those of you who are uninitiated, yes, it's backwards. The way we look at the sun is very backwards when it comes to what is west and what is east. The easiest way and there's a very specific reason for that, but I will give you the shortcut in case you can't remember why it seems like I'm pointing it backwards. If you think of a typical compass rose, right? Never eat shredded wheat, right? So east is this way and north is that way, right? And yet every time I look at the sun, I'm pointing this way as west. Well, it's not flipped. This really is west when it comes to the sun. If you are Earth and you're looking at me and I'm the sun, I know it's kind of hard to, I don't burn that brightly. But if I were the sun, this is the west side of the sun. This is the east side of the sun. The easiest way to remember that, other than thinking that you're looking at a compass rose from behind, because if I were the sun and I'm looking at a compass rose, well, north is this way, east is this way, south is that way, and west is that way. That's one way to look at it. Is that the sun it's the sun's compass rose, and you're looking at it from the backside. However, the easiest way is just to think about rising and setting. Okay, at Earth, the sun, the moon, everything, the aurora, they all rise in the east and they set in the west. On the sun, sunspots, coronal holes, everything rise in the east. They come into Earth view on the east limb of the sun. They go all the way across and they set on the west limb of the sun. So you can use that analogy to help you always remember which is the east limb and which is the west limb of the sun. even sunspots, all solar features as the sun rotates from east to west. From the Earth's perspective, sunspots rise in the east on the sun and they set in the west on the sun. Okay? North and south should be pretty easy to remember. It's the same as at Earth. But yes, so for those of you who think that I'm talking backwards, I'm not. That's just the convention that we use. And there are reasons for that convention, but that's beyond the scope of this course. But that was a good question. I appreciate that, because it is good to remind people of that from time to time. Yeah, ancients wrote their glyphs and thought like they're viewing from above. Yeah, that you're actually touching on part of the reason, the why things are defined this way. Remember, people in the northern hemisphere and the southern hemisphere view the sun from two totally different vantage points. If you're standing on the north hemisphere and you're looking at the sun with your head kind of pointing this way and looking at the sun. But if you're on the southern pole, you're upside down, relatively speaking. You're like, well, I'm too low here. You're pointing the other way. It's like you're standing on your head and you're staring at the sun the opposite way. So how do you get astronomers from both hemispheres to agree what is north and what is south, what is east, what is west? That's how they started the convention. And so there's a historic reason for that. It's because of the way the sun looks in different locales on the Earth. They had to find a way of making a convention. And so that's one of the conventions that they drew. So that's part of why it's like that. But again, I don't want to get too in depth into solar astronomy, but that's just the way things have been for a long time. Okay, so any other questions on what we've covered so far? Why does the magnetic field flip so often? The sun's magnetic field flips so often? Oh, that's it. You want a Nobel Prize? Understand the solar dynamo. We're getting there, but we don't pretend to understand it nearly as well as we should. Part of that is because the sun is completely opaque. Once you get to the radiative zone, we can't see inside. The sun is not giving up its secrets easily. And unfortunately, helioseismology, which helps us to some degree, is not always repeatable. So there are certain things that are still very difficult for us to understand. And we can't really use the planets, the rocky bodies, as an analogy because the rocky bodies with iron cores are totally different. How their dynamo is generated, like Earth's, for example, is radically different than how the sun's dynamo is generated. We believe the sun's dynamo is generated in a convection zone that is kind of closer to the surface. It's not even in the core. And so there's not a lot of analogies. And we're also beginning, as we get even better at our instrumentation, we're seeing multiple layers of dynamo. So deeper down, there's different convection patterns with a different length scale and a different time scale. And then as we get further and closer to the surface, they're getting smaller and smaller and smaller. But we're seeing these superposed convections and small convections up to large ones, and all of those are contributing to not only the dynamo, the overarching dynamo, but also the size of sunspots. There's a lot of really fascinating science going on about that right now, and we're beginning to learn a little bit more why rules like Hale's law and Joy's law, why they get violated, is because we're realizing that Hale's and Joy's law oftentimes are only applicable to the largest of the sunspots, which are the biggest, the deepest currents, and the largest of the currents of the sun, whereas the smaller currents that are closer to the surface can violate things all the time, and they give us little tiny sunspots. And so it's a separate kind of dynamo action. And it's really going to be the additive aspect of all of these little things that are in totality the whole solar dynamo. And we are easily decades off, maybe even more than that, from understanding what the solar dynamo really is. So why does it flip as often as it does? I wish we knew that. I really do. So anyway, okay. Gleisman cycle. All those cycles, by the way, are pseudo cycles. They're not precise, right? All of them kind of vary a little bit, and because they're superimposed, they all kind of modulate one another. And that's why we get the grand maximums and the grand minimums. And it also is why we get the different sizes of grand maximums as opposed to grand minimum. You know, one of the grand minimums that we were in when the Maunder happened, or the Sporer minimum, right, which is even deeper than the Maunder, those grand minimums were really tiny, right? Well, we already are in kind of a grand minimum now, but it's not as tiny. Sunspots aren't disappearing. The solar cycles are getting weaker from that perspective, but they're not disappearing altogether. And you know, people, when we talk about grand solar minimums, people freak out thinking, oh gosh, the sun is going to burn out. And it's like, no, this is just, you know, one of the times where the activity dies down a little bit, and then it'll come back and it'll get really big again. And we don't know enough about these, the modulation of these maxima and minima. We can do a lot of statistical analyses, but it really doesn't help us all that much when it comes to prediction, simply because our timescales, you know, in which we live are so much smaller than that of the sun. Plus, the sun is kind of a moving target, right? It's evolving in its lifetime. So what worked, you know, for your grandma's solar cycle just may not work for this solar cycle. So it's really hard to say, and we just don't have enough data in the space age to make really accurate assessments of that stuff. So, all right, anyway, kind of a little off topic there. So, looks like everybody seems to be on it. You like what I'm doing thus far, so I will continue. Okay, so if we talk about the solar flare myth, those of you who were with me during the discussion of the solar flares and those courses, remember Jack Gosling. He was the one who wrote the solar flare myth paper. Jack was a good friend of mine. I loved him dearly. He was also a mentor and an advisor for me. And he wrote this paper back in 1993 that basically decoupled the concept of solar flares and coronal mass ejections being essentially one phenomenon. People have thought that you can't have a big solar storm launch without a solar flare, and so anytime you had a solar flare, you'd have a CME, or you know, vice versa. And he basically decoupled that and said, no, these are two totally different phenomena, and you don't have to have one. One does not beget the other. They oftentimes happen simultaneously, but it's not a causal thing. And so up until about the 1990s, we only had, when it came to radiation storms, we only had one picture. We had the idea that solar flares caused radiation storms, and we had the two-ribbon flare, and I know I've talked about this provocative picture before. Hopefully I'm over it by now, but if you hear me chuckle, it's, you know why. But you have the flare ribbons, and then from that small localized region of the flare, you get these energetic particles shooting off, and that's what the curly, you know, the little slinkies are. That's showing particle paths, and it's in a very narrow band. It's not over a lot of, you know, a huge swath of longitudes around the sun, just in a small region. And we've really thought that that's what what was causing these radiation storms. The sad thing is that when we would watch these solar flares, I mean, this is even back in the 1940s, we would see solar flares, even white light flares. We'd study these types of things on the sun, or we'd see filaments leaving on the sun, and then we'd get these radiation storms. We'd get ground level events on the ground that we could detect. But we got these things like what we called Forbush decreases, which I will go into more detail in the next course, because it has a lot to do with cosmic rays. But back in the 40s, we didn't even know there was a solar wind. So we had we didn't have a clue there were anything like coronal mass ejections coming from these things. So for us, it was all about flares. And so we'd see the Forbush decreases, we'd see the H alpha flares, you know, we'd see things coming off in the light, the kind of light that calcium lines, for example, that we'd be able to see on the ground. But, you know, because we didn't have any space telescopes that were space-based telescopes yet. So we couldn't see really these big mass ejections being launched. Again, if you haven't seen my course on coronal mass ejections, you really should catch at least the first one, because it'll show you the evolution of how we actually learned what a coronal mass ejection was and how we discovered it. It was basically having to launch space-based telescopes to even see them. And it's just fascinating, the history of it. At any rate, so by the time we figured this out in the 90s, well, a little bit later than that, or even a little bit earlier than that, because Kaler and Hillary and Kane and others, right around the 70s, when we started realizing what coronal mass ejections were, OSO 7, for example, which was a coronagraph, or had a coronagraph on it, was launched in like was imaging chronomass ejections in the early 70s, like 1972 or 3, if I recall. And they started realizing that, oh, well, wait a minute. Maybe it's chronomass ejections that are driving some of this stuff, because when we look at images that have only just a flare with no chronomass ejection, we would see these very small, narrow extents with these particles coming out. But then, when we'd have a chronomass ejection launched with it, suddenly you could get a much wider extent of this radiation storm. So the flare didn't have to be at a particular location that's kind of coming close to you. It could be, the flare could actually be very far away. And if a chronomass ejection ends up driving, being launched with it, then if that chronomass ejection is even close to you, you're going to see the radiation storm. So they started realizing that, well, wait a minute, there's got to be two classes, that flares without the CME have a very narrow extent, flares with a CME. That CME then, as they learned, especially with the shock, it ended up being the shock, this big black line, that ended up being what was driving the particles and spreading them out in longitude and actually accelerating them even to higher energies. So what they're showing here obviously is this little hot dog or banana, whatever you want to look at. That's like the cross section of a big solar storm as it's coming out. And then the particles are streaming from that black line both out, and if you notice, some are streaming back. Some are, whoops, I'm pointing in the wrong place, sorry. Some are streaming back behind the shock, see that? Back that way. There's another one on this side that's streaming this way toward the sun. So you do get particles on that shock that are kind of wiggling through the shock and then shooting out. And it just absolutely takes a very small seed population from the flare and spreads it out and energizes it even more and just intensifies that radiation storm. Okay? So we ended up getting a two-class picture. And I guess I'll stand on this side. We ended up getting a two-class picture. We called these impulsive events, and SEP, for those of you to remind you, solar energetic particle events, we do call them SEPs, that's the jargon, okay? And they're accelerated by the flare in the corona, all right, at the sun. Now, gradual SEPs, gradual radiation storms, these guys they take that seed population that the flare gives us, and they accelerate it out into interplanetary space. That's what IP space means, if you can read that in the green, okay? Interplanetary space. So as that CME, as that big solar storm continues to move out into space, as long as it has that shock wave in front of it, that shock wave is going to continually accelerate particles. And the reason why that happens, I don't know if I've mentioned it before, I'm trying to remember, but the reason why that happens is that in a shock, because it's modifying the electric fields and magnetic fields so much through this shock. It's just like a shock wave in air, when a plane goes through it and you get a sonic boom. The point of a shock wave is to divert the air, at least in let's like planes or baseballs or something. If you're throwing a object, a projectile that fast in, let's say, air. Okay, let's say a fluid like what we have here. And as you throw that ball, or as that airplane moves through, what is happening is that if you go faster than the speed of sound in that material, in that air, the air can't move away. It can't move out of the way of this ball fast enough. So what happens is a shock wave forms in front of it. And that shock wave's job is literally to change how that air, the density of the air, the temperature of the air, and the velocity, the energy of that air, so that that air can then flow around. It then will have the right configuration to be able to flow around that ball just in time for that ball to pass. And the more time it needs to be able to convert, the more conversion that needs to be done between density and velocity and temperature, the more it needs to convert that, the further off that shock wave stands from that ball or from that plane or whatever it is flying through. So you can always tell how much faster something is than the shock speed, or than the speed of sound, let's say, in that material, in that medium, by how far off that shock wave stands from that obstacle. If it's just barely moving faster than in this case, the speed of sound, the shock wave is right in front of it. But if it's moving much, much faster than the speed of sound, that shock wave is way out here because it has to have time to be able to divert all this stuff so that the plane can fly through or the ball can fly through. Same thing in space. Believe it or not, we do have what we call a sound speed in space. Not the same kind of sound speed as acoustic. It's not the same as what you hear, but it's still considered a sound speed. And we do have those same, very similar rules. So when you have a big CME, a big solar storm driving through this interplanetary space, this solar wind, it may be vacuous and collisionless, but you still have the same properties. If the thing is moving too fast, those particles can't get away in time. And in this case, what has to be modified are the electric fields and the magnetic fields, as well as density and temperature. So what's cool about that is that suddenly these particles that are spiraling very specifically in a very specific way around magnetic field lines, their paths suddenly can change. So in a shock wave, oftentimes you will get serpentining. Instead of it spiraling, you get things serpentining back and forth and going. And what happens is that every time you go through that shock, it imparts energy to that particle. And then the particle turns around and goes back through the shock again. Oh, and it gets accelerated again. And then it turns around and goes back through the shock again. And it gets accelerated again. And boom, 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 boom. And it just goes, and the energy gets really, really high. And then at the same time, it also moves and stretches out in longitude. So the particle may have started over here. It winds up over here, and it's really energized. Okay? So that's what's cool about shock waves, is that not only do they spread out the particles in longitude, but they also impart energy over and over and over and over again, right? So that's where CMEs play these really, critical roles when it comes to energizing radiation storms and taking a radiation storm that's kind of like a, this is a radiation storm, to, oh my gosh, look at this radiation storm we got here. I mean, it ends up being, much more intense. And so we literally realized we had to start calling them two different classes. We had impulsive radiation storms, which is this here, which are mainly what we call electron rich. There's more electrons than protons in them. They have, there's a particular characteristic. So they have a certain iron to oxygen ratio, hydrogen to helium ratio. There's a certain charge state they have that really talks about, kind of where their seed population is. And whether it was in the corona or maybe further out in the interplanetary space. There's certain things. And then you see duration. Okay, this is what's important here, is duration is only hours. And the longitude, when they say longitude cone, they're talking about how far out, from the sun, right? How far out, what is the cone that they would cut? So a small longitude cone, little ice cream cone, is not very large, right? And so if you're not in the right place, you'll miss it. You won't even see the radiation storm. But as I will get to in the gradual ones, the longitude cone is much, much bigger. So you see, and then even in radio bursts, there are different types of radio bursts. Here you get a 3 and a 5. Sometimes you don't even get type 3. X-rays, impulsive, so you get a very sharp burst and it comes back down. And there's a ton of these that happen, 1,000 events per year. I mean, we get these all the time. But with the gradual ones, and I'll stand back over here more, these ones end up being proton-rich. Let me go over here. These are proton-rich as opposed to electron-rich, which actually makes them that much more biologically active. They become a much bigger deal for astronauts at Earth or for space tourists or, even people in airlines, passengers in airline flights, even regular airline flights. There's a slightly different composition, which is more for scientists than for you guys. But the duration now, look, days. Remember how I was telling you that we have, if you have a radiation storm that's being driven by a solar storm, as long as that solar storm is still coming at you and it hasn't hit you yet, you're going to be you're going to be dealing with this radiation storm. This is why it takes days, okay? Look at the longitude cone, 180 degrees. I mean, that's this wide. If I'm the sun, that's this wide. And you'll see that it's even wider than this. But back then when we did this, when Don Reams did this paper, this was, 1995, this is what we had classified. But they're even bigger than that. And of course you get radio bursts for this. You also get a type 2 as well as typically a type 3 as well. But you get type 2, type 4. Of course, type 4 is also storm particle radiation from ICMEs coming out. And then we call this a gradual. And of course you see a CME, and of course you get an interplanetary shock. A lot less of these per year, but you know what, 10 during solar maximum, that's an understatement. We get more of those, more than 10 a year, especially near solar max. And they can be pretty big. So they look different, and I think this is getting close to where I stopped last time. They look very different. If you take a time series, so that's what this is here. This is a time series where you've got, in this case, 1981, December 5th, 6th, 7th, 8th, 9th. So this is about a 4 or 5 day plot here. And then going up, okay, that up, that's intensity, that's particles, that's what we call PFU, which is proton flux units, okay, or particle flux units in this case. And so it's just intensity, how much flux. In this case, flux is, let's say, you have a target about this big. Just say the target this big. Right? It doesn't really matter how big the target is, but how many particles go through that particular target in a particular time. Okay, so this is a cross-sectional area. It's a certain area, and how many particles go through that per second in this case. Okay, so that gives you an idea of what flux is. It's not just the amount, because like if you had a total amount, then you'd have to count them all. It doesn't matter how much time. You just count how many particles you had. That's not what we're talking about. We're talking about a rate. How fast is something coming in? And those are two totally, when it comes to radiation storms, those are two totally different things. One is called flux and one is called fluence. And they're both very, very important, because one is a total dose for radiation. That would be the fluence. And then there's a dose rate. How fast are you getting dosed? Both of those things matter, and they matter differently. Okay, especially when it comes to spacecraft parts, human brains, whale migration, all of it, it all matters, and they matter very differently. So that's why we kind of keep track of them in a different way. So when we're looking at this, we're looking at intensity as a rate, okay? And then as you see it rise, you're going to see how that rate changes as you go up, as you move it forward in time, okay? So for a gradual radiation storm, in this case, you're seeing, which is driven by a CME, as you can see here, okay? So you've got that shock wave. You can get a particle storm that starts up, ramps up really fast, and then levels off and just stays high, okay, in the lowest energies. And I'll explain the low energies in just a second. But notice you've got this one, and then you've got a couple other lines over here, down, down, right? They ramp up and they slowly decay. Okay, and like I said, I'll talk about these energies in just a second. In an impulsive event, okay, we're looking at the same set of energies. Look at the difference. Okay, once again, this is August 13th, 14th, 15th, 16th, 17th. So the days, so you're comparing, you know, apples to apples here. The days are the same length. Look how much shorter, and I'm going to try to get out of the way so I don't block both of them, but look how much shorter this impulsive event is. It goes up and then down, right? Lasts part of a day. And granted, there's a decay. Okay, there's a little bit of a decay. It takes a little while. But look at the peak. It's almost the same height as the gradual for the low energy stuff, right? The peak is almost the same height. But look at the difference. One lasts a few hours. The other lasts days, right? And the reason for that, again, is because that CME, as it's traveling to Earth, is driving, the shock of that CME is driving these more and more particles to be accelerated and maintaining that level of acceleration and that level of energy. Now, what these different energies are, and just always remember this, anybody who gets interested in wondering why do we look at all these different energies. We have low energies here. I think this top one is here is, what are they? 1 to 4 MeV, yeah, protons. Anytime you have the lower energy stuff will always have higher fluxes. As you get into higher energy stuff, they're more rare. So if you have a target, you will have the largest amount of particles popping through that target of lower energy, okay? The higher energy stuff, they're more rare. They pop through less often, so their intensity is lower, okay? And when you get to really high energies, the intensity is even lower. So you can expect that for this stuff, for this top trace, okay, that's the highest intensity of fluxes. That's going to be the lowest energies. So these are around 1 to 4 MeV for protons, okay, and maybe even electrons in there too. And then down here, this trace is going to be lower, right? I guarantee this is going to be either 7 to 13 or 22 to 27 MeV. And then down here is definitely just the 22 to 27 MeV. Okay. Same thing on this one. The highest peak that you're going to see on the impulsive event here, that's going to be the lowest energy stuff. Maybe just electrons in this case. Okay, they'll peak, and they also peak in front of the protons typically. I'll get my hand out of the way so you can actually see it. That's probably the electrons. I'm not even sure I see protons there. The protons are a little bit lower here, and they come up a little bit later. There's a reason for that. Electrons travel faster than protons do, accelerate faster than protons do, because they're lighter, they're smaller in mass. They're like the motorcycle as opposed to the semi, the big semi-truck. Protons are big, heavy, you know, a lot of inertia, really slow to get moving. Electrons are zip, 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 zip. So they can zip along field lines much faster and get accelerated to their peak speeds much faster than protons can. And so they always win the race. So they always arrive before protons do, which actually gives us hope for prediction of solar proton events, and we'll talk about that in a minute. But anyway, the higher fluxes are always the lower energy stuff, and then the higher energy stuff is lower and lower. Now, the reason why that becomes important is because when we talk about radiation storms, we don't always get the same amount of fluxes in different energies. And so we have multiple ways of deciding whether we have a radiation storm or not. And we usually use 2 different energies as a marker because they sometimes behave differently. And I'll talk about that in a little while. So this is where I definitely left you guys last time, trying to illustrate here with this diagram just one Parker spiral field line coming down. And the traditional model with just being kind of like flare driven, the cone that you're seeing in this color, this is a radiation storm coming out around that Parker spiral field line. The cone is very narrow. Okay, that's what we've been talking about here. But when you use a coronal mass ejection inside, look how much you can spread that cone. Look how big it gets. That's because of the shock, the shock wave of the coronal mass ejection that's being driven. Now, granted, this is an idealized model, but look at the radical difference. Okay, you can see why we say the longitude cone of a flare, or I mean a CME-driven, a solar storm-driven radiation storm, why it can go 180 degrees or more. Whereas with the solar flare-driven one, you know, the cone stays pretty small. So you're going to get hit, you know, the chances of you getting hit by one of these is much bigger than the chance of you getting hit by one of these. So these are the ones predominantly that we worry about, plus they're proton rich. So that becomes, that's why we worry so much when we talk about coronal mass ejections coming out and we talk about, okay, whoa, we have a big flare and a big coronal mass ejection that was launched. What are the chances of a radiation storm? Pretty high, and us getting hit by it. Now, one other thing that I want to talk about before we go into all of the longitudinal distributions, because you're going to be able to see how by launching by having flares and CMEs launched on different sides of the sun, how it affects their shape coming to Earth. But before we talk about that, I wanted to mention something regarding what are energetic storm particles. Believe it or not, I don't know why we do this as scientists, but it drives me crazy. Energetic storm particles almost looks like, you know, we just accidentally miswrote solar energetic particles, right? SEP, ESP. Oh, was somebody dyslexic? What happened? No, believe it or not, these are not the same thing. It's really unfortunate that they have the same letters for the acronyms, but they are not exactly the same thing. Energetic storm particles, I believe, came from the magnetospheric field. So these are the people that work behind, they're not solar physicists, they work behind the Earth's magnetic shield, and they worry about what happens when these storms hit Earth, okay, and what that means. They really cared about what happens when that shock wave hits Earth. Now, notice in this is a time series, same thing as what we just saw before. This is time is going, you know, from left to right on this, and we've got intensity going up in proton flux units. And this is October 19th of 1989. This looks like it's about a 3-day, well, so about 3.5 day plot, okay? Those are times, that's 12 o'clock, 0 UT, 12, 0 UT. Yeah, you can see October 19, 20, 21, 22. So a few days here. And you can see that particle storm as it goes up. And again, the different traces are just simply different energies. And you can see them plotted here. The lower energies are going to have the higher fluxes. The higher energies are going to have the lower fluxes. They're more rare, okay? But don't get confused by all the lines. And what you see as you drive through this, irrespective of which line you choose to stare at, notice this bump. Bloop, it goes up and down. You know what this is? I guess the word gives it away, doesn't it? Right here. Shock. What do you think is passing the spacecraft that's measuring it right there? Think that's the shock wave? Yeah. So the energetic storm particles are literally this little bump that occur when that shock wave reaches you. And really what you're seeing, and notice, you get this radiation storm, it launches, you know, at essentially when the solar flare and the CME launch, right? That's where you see this whoosh, jump up. And notice the particle intensities continue to build up over the next few days while that big solar storm is coming at you, right? That's because you're getting all these particles from that shock wave hitting you in the face. And you're like, oh, and it's getting closer, and so you're getting more of them, and it's getting closer, and you're getting even more of them, right? So it's the intensities are building, building, building. Soon as that shock wave hits you, bam, you get hit by the most intense particles. It ramps up really high. You're in the shock. Oh my gosh, there's particles everywhere, right? Even as it passes you and behind, it's now slightly behind you, you're still getting bombarded because there's still a ton of particles all right in this area, right? But then the shock wave continues to move behind you, and whew, wow, okay, I think we're through the worst of it. Oh my goodness. And notice, all of it begins to die down. It should show you that, yes, it's absolutely the shock that is driving these particles, okay? And once the shock gets past you, things begin to calm down. So anytime you see me in my forecast where I'm talking about, okay, here comes a radiation storm. We've just gotten hit by the radiation storm, but we have a prediction of how long it's going to take before that solar storm reaches us. You've seen me say this. Okay, this radiation storm is going to be with us for, you know, the next 2.5, 3 days. Until this time, and then it'll start dying down, but it's going to be strong and maybe even getting stronger until this time. And oftentimes you'll also hear me say, well, the storm is late, but we know it's still coming. And people are like, well, how do you know it hasn't passed us and we just, you know, it just missed us? I said, because the particles are still rising in the radiation storm. Because as long as they're still rising, that means that shock wave's still coming at you. So oftentimes us forecasters will watch the energetic particles, the electrons and the protons, to watch for when that shock passes us. And sometimes the shock doesn't hit us, and you'll see an example of that. Sometimes we'll just get kind of close to it. And so this bump isn't quite as dramatic, but you do start seeing the particles going down afterwards. So we always know if this thing is about to hit us and it hasn't passed us yet because of what the radiation storm is doing. It's either going up or going down, right? Hopefully that's clear to everybody. I'm hoping. I don't know, I'm so used to being able to talk to people. This is almost hard for me now because I have to wait to see if anybody has questions about that. Does anybody have questions on this aspect? Because I want to make sure people understand this before we move on, because I'm going to start talking about the longitudinal distribution of things so that you can get, we're going to start looking at a lot of traces like this. So, no admins or moderators. Am giving friendly warnings. Yeah, you know, I think everybody here, this community has always been incredibly positive and encouraging, and it's very, very rare that we have people who are not. And people who are not, I mean, this community is very good at self-moderating. People who are rude or mean oftentimes gets pounced on by everybody else because they want them out of here, or they block them or whatever. So people who are mean have a tendency to kind of say, ooh, this is not the place for me, because they just don't get the fun that they get from other channels. I take pride in this very loving, very nurturing, very you know, curious community that really wants to learn and has a zest for learning. And so we really have a tendency to moderate ourselves very well, and I'm so very grateful for that. So thank you for if you find people who are not playing nice, then yes, please feel free to pile on until they leave. What is seed? Oh, seed. Seed population. Seed. SEED. Nice, good question. Thank you for that. As scientists, we often call a population that starts something as a seed population, just like you're seeding the ground and then a plant grows. Same kind of idea. We call it a seed population that then is kind of like the beginning of something, that in this case, the shock wave from the CME takes that seed population and grows it into something much larger. So that's what I mean by seed population. It's just I don't know, almost an affectation. I think that's why I'm not even sure who came up with that phrase, but we call it that all the time. Yeah, Peter, yeah, we do self-moderate. Appreciate it very much. Tickle me and I heart you. I love that. Yeah. Yes, thank you guys. I appreciate you guys taking care of everything and you know, taking care of each other. You're not just taking care of me, you're taking care of each other as well, and I really appreciate it. Okay. Can my weather station UV sensor see solar flux? UV, well, solar flux is 10.7 centimeters. You know, and we typically measure it, you know, TSI is typically measured in space anymore. So you're not going to get a better, you're just not going to get a better measurement than that, because the atmosphere is not going to let you. So I wouldn't try to measure the intensity of the sun on the ground. It's just not a savvy thing to do. Just because of the atmospheric, you know, issues, clouds, for example, it's a problem. Okay, so is everybody okay? Everybody get this concept thus far? You guys, I mean, it sounds like everybody does. I'm looking, everybody seems to be pretty happy. No other questions other than the seed population. Just let me know. Playing rock guitar. Man, I miss playing guitar. I used to play guitar all the time. My daughter won't let me right now. She's too young. She wants to grab my guitar and rip the strings off. What's this, Mom? Like, oh, yes, I'm jonesing to play guitar again. Okay. Is the Earth getting hammered by radiation at night? Not the sun. Yes, the Earth is getting constantly hammered by radiation. It's getting constantly hammered by cosmic ray radiation, and you'll learn that in the next class. Don't worry, the Earth is used to it. And actually, there's a lot of people that are trying to learn more about how that exactly works in terms of how it affects climate on Earth. Cosmic rays are, you know, cause cloud seeding because of the cosmic ray showers, and I'll talk about that a lot probably in the next class. And so, you know, we're in a very interesting time, because right now, I mean, I think we've, as a matter of fact, I had Mark Looper, and I don't know if Mark is on here, but he's an aerospace employee, good friend of mine, and he works in the group I used to work in, and guy is just a genius when it comes to particle radiation and instrumentation. Very savvy at SAMPEX, which was a very long-running mission that taught us so much about particle radiation and Earth's magnetosphere. And he was telling me just the other day, he was looking at crater data. This is the Lunar Reconnaissance Orbiter, and there is an instrument on it called Crater, and it's teaching us a lot about radiation, even for astronauts, for lunar colonization. We have some I think it's FEP or something. We have some kind of material, some polymer that kind of imitates skin, and we have some particle detectors underneath it so that we can see what kind of doses we'll be getting under this material that kind of gives us a little bit of a heads up about how dangerous the radiation is going to be at the lunar surface, or at least in the orbit above the moon. And he was saying that they're actually in the process of writing a paper right now, showing that the cosmic ray flux right now has peaked again. It has peaked possibly higher than the previous minimum. Now, the previous minimum, solar minimum that we had back in 2009, we reached record highs. We had 30% higher, I believe it was 30% higher than we had ever seen in the space age, because that tells you how quiet our sun has got. Because as our sun's magnetic shield kind of quiets down during solar minimum, it lets more cosmic rays in. And then when it gets big during solar maximum, it gets strong and it blocks a lot more cosmic rays. But the interesting thing is we thought we peaked with the cosmic ray intensities and made all the records last solar cycle. Mark was telling me that it's just now recently peaked above that record, which is really fascinating because this particular solar cycle, our magnetic field of the sun is flipped, and astrophysicists know this, that every other solar cycle, the cosmic rays actually have a better chance of penetrating. They're actually encouraged to diffuse into our sun's magnetic shield, diffuse into our solar system. That was last cycle. This cycle, they're being encouraged not to. So they have a less of a chance of diffusing into our sun's magnetic shield because of the orientation of the sun's magnetic field right now. Next cycle, they will be encouraged once again when the sun's field flips again. We call it a greater than zero cycle, a less than zero cycle, and it just has to do with how the sun's magnetic field interacts with the intergalactic and the charge of the particles that are coming in. It's way beyond the scope of this. I'll talk about it in the next course a little bit, but not by much. It's a heliopotential of sorts. And at any rate, so we should not have been breaking any records this cycle because, like I said, the particles are not being encouraged to diffuse in. They're actually being encouraged to diffuse outward, out of our solar system. And the fact that we possibly have now broken the record from the cycle before is pretty amazing, because that means that we're actually in a deeper minimum now than we were even in the last cycle when we broke all those records. And what does that mean for cloud formation and climate science? Wow, the implications are pretty staggering. And I wish that there were more neutron monitor folk who would kind of gravitate into climate science, because I think in order for people to understand cloud formation seeded by cosmic rays, you really have to understand neutron monitors. You need to be able to understand things like asymptotic viewing cones and stuff, and really where these particles end up hitting Earth, because it's a very, very complicated thing. And it's just not trivial to understand. And I think we're quite a ways away from understanding what the implications are in terms of climate science. A lot of people think that, well, the clouds will cool the planet, but we have greenhouse effects where the clouds actually heat the planet. So is cloud seeding cooling the planet, or is it heating the planet? I don't know. I have no idea. It's not my field, but it's fascinating to know. And there's just all these linkages that we need to make between terrestrial weather and space weather that we just haven't made yet. Not to me, in my estimation, not in any robust fashion. So there's just a lot left to learn. So at any rate, don't worry, I'm not a climate denier. I'm not one of those people. I just know that there's more to the story than we fully understand. I think anybody who says that we completely understand climate science is fooling themselves and is being very cavalier. But that's, again, for another time. So, okay, guys, I'm probably going to move forward if there's no other questions. Thank you for the very interesting questions, by the way. This is brings us into some really good discussions, a little bit beyond the scope of this course, but it does give some food for thought. And like I said, for neutron monitors and for cosmic rays, we will talk about that in the next class. So if we talk about the radiation, I've already kind of gone over this idea that solar radiation storms are longitude dependent. And here's just a really nice example of that. Again, we've got gradual radiation storms on this side, the flare-driven ones only on this side. And you can see, if you look at longitude, okay, so these are histograms. What this is they're saying the number of events up on this side. It's a bar graph, right? Number of events up in the vertical. And then horizontally, you've got 0, which is the 0-degree longitude, meaning Earth's sun line, right on 0 degrees. Anything to the west will be this direction. Anything to the east will be this direction, okay? And look, if you have a gradual radiation storm, you can see it if the flare occurs anywhere. I mean, from 80 or 90 degrees off to one side or another, the chances of you still seeing a radiation storm is pretty big. As a matter of fact, if you look, the maximum number of times that you see it is off to the west. See that? It's not even at 0 degrees. Remember what we talked about with a Parker spiral? So you see 10 events here. These are like 40, I think there were like 45 events or something. I can't remember how many Don Reams used in this particular paper. in 1999. But you notice that the peak of this distribution, the peak of this hill, okay, is actually slightly to the left. It's like to the west, okay, right here. And that's, again, because of that Archimedean spiral, that Parker spiral, you get a peak off to the west. Now, impulsive events, look, once again, same thing, a peak off to the west. But look how much smaller distribution it has. You can see events all the way to the west limb, 90 degrees, that's all the way to the west limb. If I'm staring at you, that's 0 degrees. All the way to one side or the other, where it's going off and disappearing off the west limb, that's 90 degrees this way. This is 90 degrees to the east, okay? So 180 degrees is the full face of the sun, let's say. So all the way to 90 degrees to the west, you're seeing these particles, radiation storms. They peak somewhere around 40 to 60 degrees or 40 to 80 degrees-ish, give or take an ish, okay? And then pretty much to the east limb, nothing. Anything on the east side of the sun, you just don't see it. If it's flare related only, nothing, right? This is why when the Space Weather Prediction Center sees a bad actor like a sunspot and it's throwing off solar flares, if it's on the east side of the sun, radiation storms, the prediction that the radiation storm will hit Earth is pretty low. Because granted, you'll get, there is a non-zero chance for, you know, these events, for gradual radiation storms, right, from CMEs being launched. It's non-zero. But it's basically zero for flare-driven only. And so the bigger chance you have is once that sunspot, or the source of a potential X flare or big flare, is on, and I shouldn't say X flare because M flares do it too, even C-class flares can cause these things. But most of the time it's the bigger flares. That's where the most energy is being, you know, most energy is being released and liberated. But basically at 0 degrees and to the west, that's when you're going to get a much larger chance both with the gradual and with the impulsive. 0 degrees and on to the west, okay? And so here, if anyone knows Enlil, here's a cut of Enlil. I found this, and I forget whose talk this was. This was, I think this was a talk at CCMC. I can't remember, and I apologize if you happen to be the physicist I stole this from. But I found this really cute. I might have been Yang. I'm trying to remember who it was, and if I can, I'll look it up and remember it for next time. But this is a Parker spiral, the Enlil spiral. You can see the sun is at the center here. Earth is right here, this big yellow circle. Okay, there's, whoops, come on, Tam. Get your finger in the right place. There's the yellow circle. So that's Earth. And basically by looking at this Parker spiral, and you're looking at velocity, but it's still, you can see the spiral arms coming out. Okay, what they're showing is that if you want to get a radiation storm hitting Earth, okay, this yellow circle here, you're going to have a source, or you're going to be best connected if you have a source that's kind of off to the west, which is where this little yellow lightning bolt is. They're trying to show a cute yellow lightning bolt being like, that's where the radiation storm is launched. And you can even see where these dashed lines, so if any of you ever look at the CCMC version of Enlil, you'll see these dashed lines, the black and white dashed lines. What they're showing is a magnetic field line from the sun that connects to that particular thing. So in this case, one of those dashed lines there is connecting to the yellow planet, which is Earth. But if you notice, every single one of these little assets here, whoops, I'm pointing too far, but you've got, you know, you've got Mars, you've got stereo A, stereo B, you've got all these different little planets or spacecraft. You're going to see a dashed spiral line that's connecting it to the sun. That's why it's doing it. The reason why it's showing you that, the reason why those lines are there is to just give your guide your eye so that you can see where a radiation storm would need to be launched in order to have the best magnetic connectivity through the Parker spiral to that particular asset or planet, okay? So Earth, the best place for a radiation storm to be launched will be on the west side, where that is. And if I move to stereo A, for example, now stereo A is lit up This is why I thought this was so cute. He did stereo A lit up here for this asset. And so if you wanted stereo A, gosh, come on, Tam, there, right there, that red square. That's stereo A. If you wanted to see a radiation storm hit stereo A, well, look where he has the little lightning bolt, okay? It's where that anchor is to the sun, or that dashed line. And again, now if you're looking at stereo B in this case, see where the lightning bolt needs to be? Right where that stereo B's, that dashed line anchors to the sun. Okay, so hopefully that's clear. That makes sense to you. It really does matter where you are. You know where, at least from, if you are, depending on if you're at Earth or any other spacecraft, where you are and where that source region is relative to where you are makes a huge difference in terms of what you see. And we're about to show you very specific examples of that. Okay. So I'm going to show you two different plots, right? Yes, two different plots. They're very confusing unless you understand the diagrams first. I never really liked the way these diagrams were written, but this is the way it is in the literature, so I decided I better just explain it to you the way you'll see it in the literature, other than trying to redraw them in a way that I feel is more intuitive. You would think that these plots these are time series, hopefully you guys recognize these now, with the different energies and time going across the horizontal and intensity and proton flux units going up the vertical. But you would think that because we've got the sun sitting here in the center panel, obviously there's a CME being blown out, right? And a shock, you see the shock, that's that white, kind of whitish look there. The CME is kind of this yellow little teardrop. And if you're really savvy, if you can see closely enough, you can actually make out the Parker spiral field lines that kind of come through all that. You would think that a picture on this side would be east, a picture on that side would be west, a picture on this would be down here would be the Earth-Sun line, and that's where you would be viewing things from. But no, you got to be careful. The way these diagrams are set up is that they're trying to show you if you are a spacecraft, for example, on the east side of a big ejection being launched, a big solar flare and ejection being launched right here. Okay, so let's say this is the picture of what is exactly happening right now. If that structure, okay, ends up being west of you, see, this is why it's confusing. We're on the east limb of the sun, but the structure is west of you. Then you will see a diagram like this, okay? Here's, again, time on this side, particle intensity this side, proton flux units, okay? And I'll try not to get too blurry without blocking. Come on, camera, what's your issue? Let me stand on this side. So if that CME is to the west of you, okay, when the solar flare launches and the CME launch that radiation storm, it's going to rise very quickly, okay? And that's what you see this line. I don't know if you can read it. It says West W 53. Yes, 53 degrees to the west of the central meridian from where you're looking at the sun, okay? So that means if you're staring at the sun, the CME is blowing off to the west of you by 53 degrees, okay? That is what you're seeing here. So forget the fact that this picture is on the east side. It's just showing you that relative to where that CME is, you're off to the east. But the CME is west of you, and that's the plot that you're seeing. Notice the rise is very quick, okay? So the particles rise very fast. And again, these are, the red line is the lowest energy particles. It's 1 to 4 MeV protons. The green line is 7 to 13 MeV protons, so slightly lower fluxes. And then the blue line are the highest fluxes from 22 to 27 MeV protons, okay? So lower energies to higher energies, they're all relativistic. They're all still what we consider radiation storm level particles. But the rise in all three of those is very fast. And then notice the little hump, right? This little hump here, if I can point to it properly, right there. Guess what that is? The energetic storm particles. That's the shock wave passing you. Once that passes you, the particles begin to decay. And you can see the ESP, the energetic storm particles, the best, I think, in the green trace, in the 7 to 13 MeV. See how strong a peak that is? And then the particles begin to die down. Now, why they show the shock there, I don't know. I'm not, maybe I'm wrong. Maybe that isn't the energetic storm particles. I'd have to go look, but I would have thought that would be it. Yeah, I guess that doesn't make sense because that's only a day, isn't it? So my fault. My fault. That wasn't the energetic storm particles. It just looked like it was. Because that's too fast. The CME wouldn't reach you in less than a day. So my fault. So this was actually a week. That's why. It's how many days? 1, 2, 3, 4, 5 days? I'm surprised there was a shock at all. That's pretty slow radiation, or pretty slow CME. So they're showing a shock over here. That's probably why, if the shock passed the spacecraft, they probably saw it with magnetometers or something, and that's probably why there probably was a very weak shock at this point. So you don't see any energetic storm particles. So I apologize for that. But yeah, that's a slow CME. Why it's decaying is maybe because the shock really wasn't much of a shock, and so it really didn't drive the particles for all that long. Not sure. But what's really important in this diagram is that you have a very fast rise, okay, because you're really well connected to the sun through those Parker spiral arms. That was what the whole point of that picture was, not so much about the energetic storm particles. So then if we go over here, now we're looking at basically something that's head-on, where you have a solar flare launch and a CME launching straight at you, coming straight down, straight towards you. Notice that when the flare launches, this is east 7, so you're over 7 degrees, so the CME and the flare launch just 7 degrees east of the central meridian compared to where you are. And when that flare and CME launch this radiation storm, notice the particles do rise reasonably fast, right? And then the shock hits. That's the CME finally flopping over you. Now this one is a fast CME, as you can see down here in the time series. It's only 2 days, less than 2 days since since the flare started on the 25th. This thing arrives at 26 and a half. So I mean, you're dealing with a fast CME, much faster than this other one, this west one here. That's like 4 or 5 days. So the shock is much stronger, and as such, now you see the energetic storm particles much better. Right, so you see this intensity rise just a little bit. I'm going to try to put my hands in the right place. Intensity rising a little bit. You get to where the shock wave, it peaks when that shock wave passes over you. Right, those are the energetic storm particles, and then you can see it begin to decay. All right, but the rise, notice the rise isn't nearly as fast here as it is here. Even with that weak shock, the rise time is very fast here. Because you're very well magnetically connected. If that CME and flare occur west of you, you're much better connected. Particles get there very fast. Here, it could take a day. And it'll keep on rising until that shock hits you. Okay? Now let's do this one. Now, in this case, you're sitting to the west, but the CME is launched to the east of you. So if you're looking at the sun, the CME is to the east. Okay, whoops, I shouldn't do that. I should say I'm the sun. I'm the sun, you're Earth. The CME is to the east of you, okay? And that's what this diagram is showing. I don't want to confuse your east and west messed up again. So remember, when the CME is to the east of you, when the flare and the CME are launching to the east, you're not going to be very well connected, because most of those spiral arms, if I look at this structure, most of the spiral arms are going to be this way, and those particles are going to move off this way. And if you're down here, you're not going to see all that stuff because most of it's going off like this. Okay, so what happens? Well, in a time series, here's the day again going across. Here's the rise, right? The flux intensities. Here's east 45, so this is 45 degrees east of the central meridian. And what happens is when the flare goes off, slow rise. Look how it takes days, like 3 days, 2.5, 3 days, for all the particles to slowly rise to get you. That's because all the particles are trying to diffuse across the field towards you. Now granted, they're being accelerated by the shock, but the shock really, it's fighting that Parker spiral. The Parker spiral wants everything to go this way, and these particles are trying to go backwards against it. And it's tougher. We call that cross-field diffusion. So everything goes much, 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 much more slowly. And as that shock gets closer to you, then it gets easier, because you start seeing more. The shock gets bigger, it's closer, and even if it's going by you to the east, you know, if I'm the CME, the shock is going by you like this, but as it gets closer to you, it gets bigger, right? So the chances of you getting hit by it is much, much better. So that's why you're seeing these particles rise, and you're seeing them rise, 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 rise. The shock hits. It's not quite as nice. This one, in this case, I'm not even sure if the shock actually hit you very well. The particles are still kind of rise a little bit, because actually, when a CME goes past you this way, oftentimes you're better connected once the shock passes you. And I'll show you that in the next class. You'll see a perfect example of that. When a CME goes to the east of you, oftentimes the radiation storm will peak because the particles leaking back from the shock hit you from behind. It's much easier for that to happen because now they're aligned along the Parker spiral. And I'll show you that, like I said, next class. But that's why you see oftentimes the particles peak slightly after the shock. And then once again, they begin to die down. Okay? So 3 radically different places. If the CME is west of you, you get a fast rise and then a decay. If the CME is coming at you right along the Earth-Sun line, it's a slower rise and then a decay. And then if it's east of you, it's a much longer rise, maybe not even as intense at all, and then a decay. So hopefully that makes sense. And then I will show another version of it. And then after that, I'll take more questions to see if anybody's confused. So here is, again, a different plot of the same kind of thing. Okay? Again, if you're on this side, you are staring at the sun from here, and the CME is launching to the west of you. Okay? So that's what they're trying to show. You're on the east limb looking at the sun, and the CME is launching something to the west of you. Here's an example. A time series, once again, time going by this way, flux intensity going this way. Okay? You can see the flare launches where this says West 69, W69. Okay? Look how fast the rise is. Okay? And this is actually no shock. They're saying this one didn't even have a shock. It's just the CME driving it. And believe it or not, the CME, even without a shock, just the pressure pulse can help really mess up those field lines and cause this thing to continue, allow it to continue to accelerate. Or the particles accelerate. It takes longer for these things to die down. It still takes days. Now West 27, so now we're looking at the sun from here. Excuse me, so the CME is much closer to you, right? And now, in this case, you're getting a fast rise to some degree, but then it begins to slowly creep up to the edge of the shock, because really you're just going to hit the shock. I should pull my hand down. You're going to hit the shock just barely. There's hardly any energetic storm particles at all, because you're just barely catching the edge of the shock, and then things die down once that CME passes, okay? The initial rise is fast, but then it slowly continues to creep up just a little bit by little bit, okay? Now if we do basically straight from the Earth-Sun line, so now you're looking at the sun pretty much head on. With this one that says West 9, so in this case the CME and flare were 9 degrees to the west of you. Now you're getting a better, in this case I think it's a faster CME too. It looks like a stronger radiation storm. You're getting a fast rise, but now the shock is stronger. So you're continuing to rise just a little bit, and you can see right when that shock peaks, okay, you see that the small energetic storm particles, and then it begins to die down. And once again, now you're east. In this case, the CME is now east of you. You're looking at the sun from here, right? And now this CME is east of you. So you'd expect to have a slow rise. As a matter of fact, when this flare launched, East 49, you see this dashed line right here? The particles were actually coming down from a prior radiation storm. They were still declining even after that. The flare goes off and the particles are going down. It tells you how long it takes them to diffuse over to where you are. And then slowly but surely they begin to rise again. Okay? They rise up until that CME passes you. You hit the shock, pop, it goes up. And in fact, it continues to rise just a little bit past that shock, just like I said, if it's east of you, that CME oftentimes has better connectivity when it's behind you, and it can get you from behind. And so those particles are still pretty intense even after the shock, and then they slowly begin to die off. Very different views depending upon where you are relative to that flare in CME. And us forecasters use this all the time. We use this stuff all the time to tell us, okay, where's the CME relative to Earth? How bad is a proton storm, is a particle storm going to get? Where has the CME passed us yet? I mean, there's all sorts of things we can use with the diagnostics of this to help us understand, really what the weather is going to be. And sometimes we get it wrong, and I'll show you why, because this is not a perfect system. Not by any stretch, because the fields are very complicated. There's a lot of distortion going on. The particle paths are really not known all that well. These are just kind of gentle rules of thumb that we use to try to make it all work. Gosh, and I sure hope my pants are too distracting. I'm seeing my pants are full of stars. I feel like, look, I'm cosmic, guys. I'm psychedelic today. Okay, anyway, so any questions on this thus far before I show you a few? Yeah, your pants look awesome. Digital glitter, check it out. I love it. Yeah, so funny. Okay, let's see if anybody has any questions on that. That's awesome, Mike. Thank you for that comment. Geometry of the CME magic number. Oh, magic number, well, yeah, that's interesting. It is kind of magic. I mean, and if you think that some of these CME forecasters are doing magic, I mean, I guess I shouldn't be revealing all the Houdini stuff, because these are the tricks and tips of the trade that we use to be able to pull out the predictions that we pull out. Is because we've seen so many of these things that the particles inform us about the CMEs, and the CMEs inform us about the particles, and everything is always kind of, because everything's so connected, we're able to pull out very specific aspects of the phenomena and know what that means, because we've seen so many of them that do the same thing. So why is it called a shock again? It's a shock wave. We call it a shock. It's actually a shock wave, and it's exactly the same principle that you use as an airplane flying faster, the XR-71 or something flying faster than the speed of sound, Mach 1, Mach 2, Mach 3. We actually call them Mach numbers. Believe it or not, we have Mach numbers in space. People use them all the time. I don't go into them because there's we haven't gone into that level of detail, but it's the same thing. These are shock waves. It's because in this case the CME is moving faster than what we call the sound speed in space. Now, the sound speed is not the same thing as an acoustic sound speed. No. It's an analogy. It's analogous. It's an electromagnetic collisionless plasma version of sound speed. Believe it or not, we do have a sound speed in space. We have all sorts of different speeds that we talk about, and if you're curious about that, look up magnetosonic Mach number. Magnetosonic Mach number, and that will, just Google that. You'll see all sorts of stuff come up, and most likely you'll get very lost in the math very quickly. This is why I don't bring it up. It's not critical unless you plan to do scientific research. But the physics behind why the shock wave is created is the same. It's exactly the same. It's because you've got an obstacle that's trying to drive through a particular fluid, and in this case it's the space, it's the collisionless plasma of space, of the solar wind. On the ground in terrestrial physics, when we're talking about acoustics and stuff like that, it's the air. That's a fluid. It's a collisional fluid, but it's still, there's a lot of similarities between the two. And if some obstacle is driving through that fluid faster than that fluid can get out of the way, a shock wave forms. And that shock wave's job is to change the properties, the characteristics of that particular fluid, so that the fluid can move out of the way and allow that obstacle to go through it. And that's why shock waves, sonic booms, even in light, we have this with, if something is moving faster than the speed of light in that material, there are what we call light booms, Cherenkov radiation. And they're actually literally a sonic boom in a cone, but it's like a blue light. It happens in aerogel all the time. We oftentimes detect this stuff for whatever reason. Muons, for example, going through space and then hit aerogel will give off Cherenkov radiation because they're moving faster than the speed of light in aerogel. And so we put a bunch of like CCDs and PMTs and all these light detectors around them to be able to detect this very low blast of light in this little blue cone that it creates as the particle goes through the material. And it literally is a light boom. Same kind of physics, different, different thing, but same kind of physics. Shock waves always form to be able to divert the flow of a fluid so that it can go around that particular obstacles. Okay, you can look up shock waves for anything, and you'll be able to get the same kind of basic understanding, irrespective of whether it's shock waves in the air or it's shock waves in space. Same kind of idea. Don't let the whole thing of a shock or a shock wave, intimidate you. It's really the same kind of thing, and it's just part of how nature works. It's kind of cool. So any other questions on or anything that might be confusing about the diagrams that I've gone through, or how we kind of read radiation storms in space? I'll give you guys a couple seconds to. I answered a couple questions, but sonoluminescence, yes, that's one of the many cool aspects of this kind of physics. Looks like everybody's good. I'll keep my eye on it. And now I'm going to show you just some other examples, right? Not trying to do the diagram anymore, but just showing you some examples of easy stuff and some examples of hard stuff, so you can get an idea of where these rules work and where they break down. Let's see, what type of instrument detects the shock wave from the sun? Plasma instruments can, because they detect the changes in the plasma. So anything that measures temperature, velocity, and density. These are particle detectors, typically. We have low energy particle detectors as well as high energy particle detectors. The energetic particle detectors detect the shocks because they see the energetic particles, just like we're talking about. Magnetometers check or can see a shock wave because you have changes in the magnetic field direction. Electric field detectors will detect changes in electric field direction. You put them all together and you go, that's a shock. And there's all sorts of things that occur in space that can look like shocks, like discontinuities and things like that. We have rotational discontinuities, tangential discontinuities, all sorts of different types of crazy things, but there are only certain ones that follow the right physics in Maxwell's equations and other Vlasov's equations, other shock physics, kinetic physics equations that have to be certain conditions have to be met in order for it to qualify as a shock. But we've got a lot of theory, and it agrees very well with the observation. So we can pretty much unambiguously know if we're passing through a shock. Now, granted, if something is on the hairy edge of shock formation, because we have something called like steepening into a shock, where the plasma is right at that hairy edge of forming the shock, where it's really close, and that is, so there are some times where it's kind of hard to tell if something is a shock. But for the most part, we're really able to tell. Plus, there are some standing shock waves in our solar system. For example, the bow shock at every planet. The solar wind passes over all the planets in the solar system faster than the speed of sound. As a matter of fact, the sound speed is surpassed with the solar wind really close to the sun. It becomes supersonic. Really close to the sun, excuse me. And so all of the planetary bodies have what they call a bow shock in front of them. It's literally a shock that stands off in front of the big shield, the magnetic shield in the case of Earth. In the case of Mars, it's a shield that stands off not so far, but in front of the ionosphere. Mars doesn't have a big magnetic shield, so it's actually the ionosphere, its upper atmosphere, that stands off the solar wind. But there's a bow shock in front of it. Comets have bow shocks. All bodies, as the solar wind blows over them, have bow shocks in front of them. And we measure them all the time. And there are people who get PhDs in just looking at bow shocks of different bodies. So there's a lot of interesting physics that's done there. Does shockwave have any effect on health or electronics? Yeah, in electronics it can. And there's a lot of implications, and I don't really want to get into the details. There's a lot of implications of bow shocks, because at least for the Earth, for example, we've had the bow shock move in and out, depending upon how much the magnetic field, or our magnetic shield, gets compressed. We've actually had satellites in geosynchronous orbit actually go past the bow shock. When we have a really big storm, you can actually get it to pass past what we call the magnetopause, but also there have been a few instances where the bow shock has even been passed, so that these spacecraft in certain orbits that were inside Earth's shield at one point actually stick outside the Earth's shield. And so it's pretty crazy. As far as affecting humans, maybe a small dose of radiation here and there, depending. But most of the stuff for a bow shock, it's not creating a bunch of energetic particles at really high energies like you get with solar radiation storms. They don't have a seed population to begin with, so all they're accelerating is solar wind particles. So it's not accelerating them to as nearly high of energies. So it's not as big a deal. But yes, there are a lot of people who study this stuff. Force shock, ion electron force shocks. There's this whole region that people study. Most of these people are magnetospheric physicists, but they study mostly the phenomenology. I don't think they study it nearly so much for the health and safety of spacecraft or astronauts, because I don't think it's that big a deal. Yeah, I don't recall any studies regarding biological issues or health and safety of satellites. But that's a good question. I wonder if the energies could ever get high enough. It's not my discipline per se. I mean, I don't study it to that level of detail, so I don't know. I might be wrong, but I don't. My knee-jerk reaction, my perfunctory response is no, they don't cause that much of an issue. But I could take a look at that. 101 question: what affects the speed that solar wind travels? Ooh, what affects the speed? Well, coronal holes, definitely. It's really how the, gosh, how do I talk about this? Man, that's Parker Solar Probe stuff. We're learning that right now. Classically, we always talk about the equatorial solar wind and it being pretty slow. And then when we get into the coronal holes being the extent, typically in solar minimum, you have the coronal holes are pretty much just polar. The polar regions of the sun are really where fast wind emanates. And we found a lot about that with Ulysses. But then as you go through the whole solar activity cycle, these polar coronal holes actually kind of reach down to the equatorial regions. That's why you end up getting, these big extended coronal holes in extended latitude, and from these coronal holes comes very fast solar wind. The Parker Solar Probe getting so close to the sun is really beginning to kind of change our whole fundamental concept of what creates the solar wind and how it's created, because what becomes a really smooth kind of streams of solar wind, either fast streams or slow streams, here out at 1 AU, at Earth, for example, or even further in a little bit. You get really close to the sun, and all that stuff goes away. I mean, the magnetic field isn't nearly as smooth. It's folded in on itself, and we're seeing jets and spurts of solar wind that are fast and slow and fast, and it's much more sporadic. And somehow there's all this reconnection or something that's happening in really close to the sun, so that by the time it gets out to us, it's all smoothed out. And so what we thought originated from the sun in these really smooth streams, we're finding out wasn't smooth at all. The sun is just spurting this stuff out like crazy in all sorts of different ways. So I'm afraid, trying to answer that question, if I answered the question with the classic, well, we have coronal holes and we have these smooth streams and stuff like this, I'm afraid we're literally in the middle of refining that paradigm and changing that paradigm to something else. And I think really I can't give you a decent answer for that question anymore until we get a few more years into the Parker Solar Probe campaign, which makes it a very exciting time, to be honest, because it is absolutely redefining our understanding of how the solar wind is born. And so stay tuned. Better answers are coming, but the old answers are old. They're passé now, strangely enough. Okay. Let's see. Yeah, I can't talk about lightning right now. That's a collisional plasma. It is a plasma, like space plasma is a plasma, but it's a collisional plasma. In space, we're dealing mainly with collision-less plasmas, which is why aurora looks so different than lightning. Lightning is all, you know, and ratty because it's banging, particles are bouncing across and off one another. Aurora is very smooth, flowing like a river. And the reason for that is because it's collisionless mainly. So it's a different you know, different governing phenomena, or different governing physics that control one or the other, and that's a slightly different class. So we can talk about that some other time. Are you aware of vitrified stone fortresses of Europe? No. And the other megalithic structures worldwide that show clear signs of vitrification and melting from obvious intense heat? No, and that sounds like geology or geophysics, and so, you know, I have a degree in geophysics, but it's just more based for the planetary science I have. I'm not a geologist at all, so that's beyond my expertise. So, yeah, you say geology. Forbidden archaeology researcher. Do I believe that space weather-related radiation storms are responsible for that? No, probably not. No. The reason why radiation storms are just so, you know, it's so tenuous. Space weather is such a great thing, and it's going to impact us to a monstrous degree as we begin to leave the rim of our planet. But as far as things that are occurring on the surface of the Earth, man, the Earth, the geographic and the forcing from geological, you know, phenomena is so much more intense. So I would think magma and you know, lava and volcanoes would have a much bigger effect on something like that than radiation storms. You know, radiation storms may affect cloud seeding, but they're not going to be burning and causing intense melting, you know, at least not on a time scale that humans have been around. You know, maybe the sun did that when the Earth was just forming and we had these, you know, massive flares when our sun was far more unstable than it is now. But our sun is really reasonably well behaved anymore, and so, you know, otherwise we wouldn't be here. So I wouldn't look. That wouldn't be my primary go-to for those types of phenomena. Space weather may play a role, but if it plays a role, it's so small that, you know, you first have to decide what the big role is in order to you know, solve that problem, remove it, and then you can start looking at the underlying smaller effects, which is space weather is probably one of those. And that's the way it is with a lot of things in terrestrial science. Space weather is a much smaller effect than a lot of the terrestrial forcings. So yeah, my gut reaction would be no, probably not. Would a comet or asteroid or meteor shower have a negative impact on a solar storm within its travel between the sun and the Earth? No, as a matter of fact, it's the opposite. Man, I at some point I will show you guys some really cool imagery from the HI imager on stereo. We have comet tail disruptions, for example, that are really cool. A solar storm will come by and you have this beautiful comet with its comet tail, and a solar storm will come by and just rip the tail right off that comet, just like a gecko. And you'll watch the whole tail go blip, and the solar storm will just take it right with it. And so the comet keeps going and its tail is gone, and then slowly the comet grows its tail again. It's really cool. So solar storms actually have a bigger impact on the comet than the comet has on the solar storm. Remember that these solar storms are massive, right? The comet is like a, you know, needle in a haystack. Yeah, it doesn't care. So it's more like that. You know, it's not that the solar storm is going to destroy the rock, the nucleus of the comet, but it sure will rip the tail off. So it's kind of cute. So yeah, so it's really the opposite. Steve, or auroras reaching ground level? No. Remember, auroras, those are low energy. Believe it or not, that's solar energetic particle events, radiation storms, do not cause aurora. Okay, they cause cosmic ray showers, totally different. And we'll talk more about that in the next class. Aurora, believe it or not, is caused by much lower energy particles. And there's still particles, there's still protons and electrons, mainly electrons, but it's the same kind of electrons that run through, your fluorescent lights at home, right? That's really what it's doing to the upper atmosphere, is it's turning your upper atmosphere into a neon beer sign, and the different colors are because it's the different molecules or atoms that it's exciting. But these are much lower energy particles. These are kiloelectron volts, so KeV, not MeV or even GeV. We're talking, those are orders of magnitude, multiple orders of magnitude higher. So definitely don't confuse radiation storm particles with just the much lower energy stuff that causes aurora, because they're completely, fundamentally different. But neither of them, the primary particles, ever reach the ground. Muons reach the ground, but the primary stuff, the protons that come in, never reach the ground. Now, you can get the primary particles if you're at a high altitude flight. Sure, you can actually see them, or not see them, obviously you can, but you can get hit by them, and we've measured them. And then you also get all the daughter products from the cosmic ray shower. But most of that cosmic ray shower does not reach ground, not at Earth. At Mars, however, yes, all the way to the ground. Mars has very tenuous atmosphere. It's nothing like here on Earth. Our atmosphere protects us. Cosmic ray showers from solar radiation storms or from cosmic rays themselves, they penetrate all the way to the ground. And that's something that is going to impact us tremendously when we start thinking about Mars colonization. Because the idea that you could actually go to Mars and stay there for an indefinite period of time, I've even heard people talking about retirement homes on Mars. People in their older years want to go retire on Mars, and they're going to live out their days on Mars. And I'm going, really? Well, your days are going to be pretty short then, because you're constantly being bombarded by cosmic rays. And then when big solar energetic particles, these big radiation storms come, you'll be bombarded all the way on the planet with them as well. Unless you dive in your underground bunkers, you're going to be dealing with really high doses of radiation. So living out your life on a Mars environment is nuts. It's just, you're going to get sick. You're going to have you're going to have radiation sickness, and you will die most likely of too high a radiation dose. On the moon, it's even worse, right? Because the moon has no atmosphere. What's protecting them? Nothing. So people want to have these long-term, lunar colonies on the moon and have people stay there for years upon years upon years. It's ludicrous. I mean, even astronauts protected in the lowest part of Earth's magnetic shield, right? So they're in the most protected part of Earth's magnetic shield for radiation storms. Those astronauts in low Earth orbit, they've got a 5-year active career. Why is that? Because they get too nauseous? No. Because the zero-G environment's too hard on them? No. Because they get their radiation dose, their lifetime radiation dose in 5 years. They're considered radiation workers, just like pilots are, at least in the United States. Okay? Our bodies were not designed for space, and space is a very hostile environment. And if you watched the last class, you saw how the Apollo missions, how they got lucky, because there were quite a few radiation storms that occurred during the Apollo era, and we just didn't have anybody up. We didn't have an active mission when these radiation storms occurred. But there was one in particular that would have killed everybody. They would have all gotten a lethal dose. Imagine being in an EVA suit, walking around playing golf, or being in your dune buggy, and suddenly your skin begins to itch and then burn. And then you feel like you're being cooked, microwaved right there on the surface of the moon. Yep, that's what would have happened in 1972. The astronauts would have gotten a lethal dose if they had been, I think it was like either 1 month prior or 1 month after the mission actually went. So look at my course from the last time, because I actually talk about that, I believe. All right, let me move on. I'll take maybe one more question. Can the particles penetrate up through the ground and into the soles of the feet if you're bare feet? That's cute. Conceivably, yes, but it'd have to come the right way. There is a question about, on the lunar surface, there is a question about the neutron albedo. That's another thing that Crater has been, I remember I mentioned Crater before. The Lunar Reconnaissance Orbiter has a particle instrument called Crater. One of the things that Crater has detected that surprised everybody was that there was actually a very measurable and a higher intensity neutron albedo from the moon than we thought. And that comes from, apparently from the sun's UV radiation. Remember, there's no atmosphere. The UV radiation hits, and the EUV radiation hits the surface, that lunar dust, and it's liberating neutrons. Neutrons are hard to stop, and they're very dangerous. So they're getting a higher dose of neutrons, of radiation from these neutrons that are being liberated just because of the sun's ultraviolet rays. How much of an impact that's going to be, I don't know. I haven't seen a lot of studies, but Dr. Byrne Blake, who's very well respected, and who was one of the, he might have even been the PI of Crater, had a conversation with me about this, and that was one of the big surprises of Crater, was that they had this neutron albedo, and what were the implications going to be for astronauts on the moon? Don't know. A lot of unanswered questions. There's a lot of complications that we have not sussed out when it comes to especially long-term colonization of any planet. And people are being very cavalier when it comes to radiation. And I think it's going to bite us in the butt, to be honest. But, you know, what can I do? All I can do is teach courses like this and pray that you know, we can raise awareness enough to get people to start talking about it more, so that we can be more careful and not hurt anybody, you know, or not set up unrealistic expectations for long-term civilizations and colonization. Even though it sounds really cool and it's all this kind of stuff, let's be smart about how we do it to make sure we keep everybody safe. So that's why radiation storms are such an important part of space weather, such an important part. They're invisible, and so people think they don't exist. And we got very lucky with the Apollo missions. And so it causes people to believe that, you know, we'll be fine, but we really won't. We really have to take it more seriously than we have. Jerry, how long will it take solar storm to hit Earth after watching it? She just spent 45 minutes explaining that. Yeah, I know, I should move on. Thanks, Jerry, I appreciate you telling me that. I really should get on here, or get moving on, because I'll sit here and take questions forever, you guys know that. Can you hide live chats from your live display? They block the screen view. Yeah, I think you guys can, can't you? Can't you guys do that? There should be a way that you could minimize that. I don't know. Anybody help them figure out how to do that? Okay, so let me get to this. Let me give you a few more examples on radiation storms, and then I'll show you some examples, some real neat examples of how big these things can get. Okay, so let's talk about an impulsive radiation storm. This is where we have good connectivity. So this is when an impulsive radiation storm, so just a flare, not really a big CME coming after it. This is when a storm is launched to the west of you. So it's right along that Parker spiral, okay? Look at these two examples. Look how fast, okay? And again, you've got all these different energies, and in this case, all these different traces. It doesn't really matter, you know, you can't really read. There is a label here that's showing all the different energies. And my gosh, I don't even know if I can read it. No, I can't. And it doesn't matter. It's actually, it's not even in a format you can read. It says level 0, 1, 2, 3. So this is some raw data. But look how fast, even in all these channels, look how incredibly fast the peak of this storm occurs, right? With really good connectivity to the sun. So all of these energy channels slam up right away and then die down reasonably quickly, okay? Here's another example, okay? Good connectivity, rise real fast, you get a little bumps and wiggles through here. That has to do a lot with the interplanetary magnetic field, what it's doing. Some people think that this has something to do with maybe the way the seed population is. There's still arguments as to whether or not that's variations in the seed population or variations in what the magnetic field and electric field are doing, but then it goes all the way down, okay? Oh, and I'm seeing my green screen is changing. It was cloudy earlier, and now it's getting sunny, so my green screen, if it bothers you too much, I see a little bit of it coming on the line, yeah. If this shady thing bothers you too much, I'll recode my green screen. So here's a gradual radiation storm, and you'll see a really strong ESP from this one. And in actuality, you can actually see we were actually coming down from a first radiation storm. And then this connectivity isn't quite so great, so when the flare hits, you can see it jumps up a little, right? And it continues to rise and continues to rise and continues to rise, and then wham, we get that ESP. Okay, and then as soon as that means that the CME has hit Earth, or hit your spacecraft wherever you are, and then it begins to die down after that. Okay, so that's another example. Now, in that case, again, we weren't quite as west, that the connectivity wasn't quite as good because it took a longer time to rise. Now, here's another one. Here's a poor connectivity one. As a matter of fact, it's so poor that you see the ESP, but it's really ratty because the shock doesn't really hit you. In other words, this thing, it rises. You see the rise in all the different energy channels, kind of off from one another. You see the rise, but look how ratty this ESP is. Kind of just cuts through and then slowly dies down. Likely, in this case, you can tell that the CME passed you, but in a forecaster's vernacular, we might actually be waiting for the CME to hit, you know, and everybody's like, Aurora, Aurora, we want Aurora, right? And we keep watching the interplanetary, you know, the upstream monitors, and it's just not coming, and it's just not coming, and it's just not coming. We look at the energetic particles, and we say, yeah, it's coming, it's coming, it's coming, it's coming, and then it gets to here, and we're like, uh-oh. Have we seen anything in the magnetometers yet? Have we seen anything in our upstream, you know, monitors? Has the CME hit? And everybody's like, nope, still solar wind. And we go through here, and then we start going down, and we're like, oh, bummer, guys. We're not going to get any Aurora. Too bad, because the CME passed us. We missed it. And that's how you can tell with the radiation storm particles that, yes, the CME was close, but it didn't quite hit us. Okay? And then, of course, here's where all bets are off. What in the world? This is what happens when you get multiple events occurring, when you get a really bad actor on the sun, and it's just firing off a CME and a flare, and then a radiation storm, and then another one, and boom, boom, boom. And you can't even calm down from the first one before you get the second one. And Lord knows, when you get hit by the second one, it looks like good connectivity because the thing ramps up really fast. But then it continues to ramp up. But now you've got two sets of radiation storm particles that are being accelerated, because the first one ran into the second one, and you know, it's just like, ugh, how do you tell what's going on here? A lot of times you can't. So, you know, the rules I give you are great rules, but not always, because sometimes things get too complicated for us to figure out. Okay, and here's part of why, right? Here's let me get on this side for this one. So in this case, what we're looking at is, again, this is a more complicated version of Enlil, believe it or not. This is kind of a high resolution one that actually is not just what we call the cone model. The ones that we look at for real-time coronal mass ejection or big solar storm coming to Earth that we forecasters use that can run faster than real time, they don't have any magnetic field in them. They're not this complicated. This version of Enlil we couldn't run in real time. It takes days and days and days to run this model when it's got the magnetic field in it. So what you're looking at here is you're looking at the sun. I think this is velocity. Yeah, it's velocity. They've even mapped the speed of the solar wind right onto the surface of the sun, so where it's emanating from. The blue is slow, so that's, you're seeing up here with the if I can put my hand in the right place, you're seeing kind of the coronal streamer belt. If you're worried about what that blue line is, that's kind of showing where the magnetic neutral line is on the sun and where all the origin of the slow solar wind is as we see it at Earth. And then it gets faster as you get up closer to the poles. That's why you start seeing it turning, you know, yellow and sometimes red. Same thing in the South Pole, but you can't really see it because we're looking kind of down from the North Pole of the sun. This whole area is the ecliptic plane, so it's the flat disk or that where all the planets orbit. And what you're seeing, you're seeing Parker spiral, Archimedean lines coming out. Here's a fast wind stream in red. Okay, here's a slow solar wind stream in blue, right? And then what I'm standing in front of is a big coronal mass ejection. Okay, and I'll try to get out of the way. Now, the front of that black area, and I'm sorry if you hear a plane flying by, it's a really big plane, loud. So if you hear that noise, don't worry, it's not you, it's noise in here. You see that big black line? That is the shock, okay? That's the shock wave. The dark red here is the fast solar wind. That's basically the fast part of that CME. the actual kind of like banana looking thing here, that's kind of a white thing, that's kind of a contour of a main, probably a density blob that is the main part of the CME that's driving this whole shock, okay? And all of these contours that you see, the little black lines, those are all magnetic field, wait, no, my fault. They're all velocity contours. I had to slow down there. So basically you see again, they're ISO, what we call ISO contours. That means each one of them dictates a speed of solar wind. So you can see in the front of the CME where it's red, that's where the fastest part of the CME is. But there are some areas where it's slowing down. And even if you look over here to the east part of the CME, over on this side, you kind of see it the contours get a little bit bent because there's some fast solar wind, slow solar wind kind of competing. And so what's happening is it's beginning to kind of bend things around a little bit. And so what they've done is they've drawn a single magnetic field line through this structure, because they track the field lines too. They just aren't going to show a whole bunch of field lines on top of this plot because it'll make it too complicated. So they just showed one magnetic field line trace. And you can see as it traces through this structure, look how bent it gets by the CME, bent out by the shock, and then out. Okay? Look how complicated that path is. This is what radiation storms have to deal with. Okay? They have to deal with, particle paths have to go around this stuff. So you can imagine if you have a bunch of magnetic field lines being all bent and crazy like this, look how complicated the paths can get for these radiation storm particles. And so it becomes extremely difficult to always, have a clear picture of what's going on. This is one of the reasons why this stuff gets so complicated and why it's so hard to predict, is because the magnetic field can get extremely complicated. It's not like this. I wish it were like this. I think we all wish it were like this. Here's magnetic field lines showing, look how pretty that Archimedean spiral is in that case. They're beautiful. I wish it would always look like that. We'd be able to do radiation storms no problem, right? But the problem is we have structures like this that get in the way, right? Here's looking at a CME, or the cone model of a CME. Look, it's not a perfect slinky, and this thing is kind of bent off to one side, and it's, all weird and stuff. And look at it from this perspective. Here's looking at it through the tube. You're kind of looking at it coming at you, and you're trying to thread the needle here. You can see there's one leg right here coming through, and then the other leg is on the other side coming through the other way, right there. So and you see field lines being bent around the structure. See the red field lines being bent around. So there's all sorts of things that can cause serious distortion and serious issues when trying to read these radiation storms and what kind of fluxes we're going to be getting and when we're going to be getting them. So as much as we like to have that beautiful picture, we don't always have that picture. And it makes, if we talk about radiation storm predictions, it makes it really tough. It's not easy to do radiation storm predictions because of this. But we do, luckily, have, in many cases, we have help. Remember I was talking about electrons, and electrons, because we have radiation storms that have protons and electrons, and they're both accelerated at the same time, but because electrons are like the little motorcycles and the protons are like the big semi-trucks, if you say ready, set, go, who do you think is going to get off the line faster, right? The motorcycle, right? Well, those are the electrons, and because of that, they arrive at Earth first. And their profile, especially their rise rate, how fast they increase in intensity, can give us an indicator of what the protons are going to do when they arrive. And so we've actually created prediction models, and this one is one of the ones that you can actually get at the CCMC if you actually look at this particular. If you actually look at, I'll show you right here. I think the next plot. Yeah. So you can get this particular model that you can see things like here. If you go to the ISWA modules on the CCMC, you can actually get this release model, and you can see what type of predictions it will give. And really what it's doing is that it's taking the whole concept of electrons coming out from radiation storms and hitting Earth first, or hitting the any detector, upstream detector first, and they can arrive within 15 minutes 15 minutes to half an hour of a radiation storm being launched, where the slower ions won't, see, you can see them being launched here, the slower ions don't actually reach Earth for maybe up to an hour or more, depending upon how they're connected. Remember, if they're connected on the west, if it's a west limb launch, then they'll arrive quickly, but they'll still arrive much more slowly than electrons will. So you can see the rise of the electrons and know how fast that the protons are going. I mean, know how steeply intense, how fast the proton rise will be as well. And that's kind of what they're trying to show here, is that when the ions arrive, they'll have a very similar shape. Their profile in the rise time plots will have a very similar shape as the proton, or as the electrons did. And so you can kind of get an idea. Now granted, it gives you what, 15, 20 minutes, notice it's not a lot, but it's enough for astronauts. It's enough for Johnson Space Center to say, okay, guys, go dive under. This looks like it's going to be a big radiation storm, because the electrons are rising very, very quickly, and it's a prompt arrival, as we oftentimes call it. And so you guys need to get into your bunkers now. You need to get into that, where that water storage or anything. And we'll be using these types of warning systems, guaranteed. We'll be using these types of warning systems when it comes to colonization of the moon. Definitely, because it doesn't give us much time, but it gives us a little bit of time for people to get to the water wall. In the lunar, they have these protective walls where you've got water storage and you hide behind the water storage, or you go into your underground bunker or something like that and hide underground and ride it out. So it gives us a little bit of hope that we have some level of protection, but it's definitely not a solution at all. But it does give us a little bit of help. And so, as time goes on, you can, and our sun wakes up and you start seeing radiation storms again, you can definitely look at the ISWA modules, because you'll see the release model. SWPC has not adopted this model yet. I don't know if they will. I don't know if it's going to end up going into operations at the Space Weather Prediction Center, but it'd be nice if we had something like that. Okay, and so for those of you who remembered last time, I actually gave you a sneak peek. One of the things that I wanted to, before I go into examples, like specific examples of big Carrington class events that we've had recently with radiation storms, I wanted to give you a neat little thing to leave you with, which is the whole concept of what radiation storms can actually be. And as you can see here, just even from impulsive SEP events, you can have the whole gamut when it comes to charge over mass ratios. You can actually not just have protons and electrons, which is the bulk of what this stuff is, but you can have all sorts of different elements coming out, right? I mean, that's kind of how our sun, not just supernova explosions, but even in these solar energetic particle events, these radiation storms, we create everything in the periodic table. Okay, you can see all the different elements here with all these different atomic masses. And we actually call them ultra heavies. And if you can see over here, if I stand over here, here's a really good plot. You can see counts per bin. So these are what we oftentimes call single rates. And you can see there's a lot of singles here that's just going up. So in other words, the number of particles we're getting, not a rate, but total number. They're just doing counts over a particular time. So this is probably affluence. And the intensity goes up, right? And then, or the count number, the count rate goes, or counts go up, total counts go up. And then over here is the mass. So this is the atomic mass, AMU, atomic mass units, as you can see, from very low masses all the way up to the highest masses in the periodic table. And you can see the distribution, of course, is very, you expect all the low masses to be what you see. You see a lot of hydrogen, a lot of helium, iron, oxygen, carbon. Okay, you get all that. No, not iron, sorry. Oxygen, carbon, that type of thing as you get further and further down. Then you get into things like iron and stuff like that. But look out here. Look at this ultra heavy set out in here. Okay, you see that I'm trying to circle it right here. See that? Those are the ultra heavies, that little bump on tail distribution. Anybody know what 197 atomic mass units is? Anybody recognize AU? Anybody know what that is? I'll show you on the periodic table if I can get out of the way. See if I can find it. This one right here. AU. Anybody know what that is? Gold. Solar alchemy. Very good. It's gold. So when you think about solar radiation storms, okay, think about the radiation, think about the scary bits. Sure. You know, it's scary. It could irradiate us. But it's also raining us with gold. It's raining gold on us. Kind of neat, huh? They're making us richer. So every time the sun shoots off a radiation storm, just say, ah, gold from heaven. Because that's what it's raining on us with. Pretty neat, huh? I always thought that that was a neat aspect of radiation storms. So not every part of it is scary. There are some parts of it that are kind of mesmerizing and awe-inspiring. So take that home with you. Yeah. Pretty cool, huh? Especially in a time with, you know, the economy shutting down. Now we need more radiation storms, right? We got to get rich. The stock market's collapsing. What are we doing? Let's come on, more radiation storms, please. I'm gonna stand outside and get peppered and sprayed with gold. Give me my gold dust. Oh, what a world we live in, huh? All right, let me see where I am in all of this. I have a lot of charts, as you can tell. Don't worry, I'm not going through all of them today. I could go through another 1, 2, 3, 4, 5, 6, 7, 8, 9. Do you guys want me to go through 9 more charts? Or should I call it a day and just answer questions and save all that stuff for next time? What I was going to go through is a bunch of just examples of some radiation storms at Mars, show you maybe a Carrington class event, that type of thing. Are you guys tired? Or are you guys ready to go a little bit longer? Or what do you think? Why don't you let me know? I'm going to take a little sip of water here while you guys... Yeah, water is an amazing irradiation buffer. It is. It's wonderful. Gold dust woman, yes. Call it a day? Okay. Keep going. This is a welcome distraction. Most people want me to keep going, huh? Okay. Others need time to digest what you've presented. What I could probably do, because this won't take that long, but what I could probably do is when I start the next class next time, I could review just a little bit of this. So for those of you who want to hang on, I'll go ahead and go through this set of charts. Like I said, we're really only just going through examples now that just kind of give you an idea of, give you a little bit more food for thought when it comes to how big these radiation storms can be and what we need to think about when we're doing colonization in places like Moon and the Mars. And then the next class will be mostly about cosmic rays and how they fit into the picture of solar, these solar radiation storms, how they're this similar and different. So I can probably, go through the events again as a little bit of a review. So yeah, I'll go ahead and keep on going because most people, I'm here for the long haul. I've seen more people say continue than people say stop. Do you have a YouTube where you can go take a break with the rest of us to watch? What do you mean? I have no idea what you mean. You're probably not talking to me then. I'm ready for a break. Well, feel free. So those of you who want to just, who feel like you've been drinking from a fire hose, go ahead and I won't give you any more information about this. You've learned everything that's fundamental about solar radiation storms. Now I'm just going to go into a couple of examples for those who are diehard, and I will review those in the next class as well. Maybe not in quite as much detail, but I'll review them, so you'll see that. So yes, please feel, for those of you who decide that you want to take a break, feel free, and I'll see you guys next time. But for those of you who want to continue, I will show you these next 9 slides that just kind of like the cherry on top. It's really not just a little bit more food for thought. Okay. Thank you, Gary. That's very kind of you. Does Elon Musk know about the radiation? Oh, yeah, we know he does. I think he's just so driven to make things happen that he I don't have time for trifles. Or if he shares everything about all the problems, then he'll never get to where he wants to go. And so I see both sides of the coin, and it's, you know, it's an issue. It's an issue, but I'm not sure what the answer is for that yet. Okay, Vince, thank you. I appreciate that. See you next time. That sounds good. And you're right, Shasta. See you next time if you're leaving. Don't worry, there's not going to be a test after this, so you're fine. Okay. All right. So for those of you hardcore who are planning to stay and continue to take your mind off of COVID-19, wonderful. Now we're going to have a little fun. And let me go back to presentation mode. Okay. So what I had mentioned to you guys earlier was, remember I told you there's a reason why we look at multiple different energies of these radiation storms, and the reason for that is because different energies have different activities. We care, just like we care about dose and dose rate, we care about how much radiation dose someone gets. We also care about how fast is it accumulating. That's why we look at flux and fluence, because they have different activities, both biologically and with like spacecraft hardware. Different energies have different activities as well. Different energies penetrate differently and they deposit energy differently. And I'm not going to go into all the details of that. It's actually counterintuitive. The lower energy stuff actually can cause more problems than the higher energy stuff can, depending upon what it is you're looking at. But because of that, we end up having multiple ways that we classify a radiation storm. So at the Space Weather Prediction Center, when they look at a radiation storm, for example, you'll see, and you should know these plots by now. This is a time series plot, right? Here's time going across on the right, intensity and proton flux units going up on the vertical. And this is a logarithmic plot instead of a linear one, so that's why you see the lines kind of getting close together and then big again and then close together and big again, separate again. That's just the reason why we plot it this way is because there's a huge dynamic range. These particles go up orders of magnitude, and if we plotted it on a linear scale, the plot would be like way off it'd be so high up, it'd be like climbing a mountain trying to read the plot. So we crush the vertical scale down, and that's why you see the lines start big and then get really close together and then get big and really close together again. We're going up orders of magnitude when we do that. But it allows us to plot the lines in such a way that we can actually read them. And so the blue trace here is low energy. This is the 10 MeV channel, as you can see. Remember, low energies, relativistically speaking. The lower energy side will have the higher fluxes typically. And then the higher energy like this, so there's 10 MeV in blue. In red, this is, oh gosh, what is this? 30 greater than 30 MeV. In yellow, it's greater than 50 MeV, and then green is greater than 100 MeV. These are what we call integral fluxes. It's not the only kind of fluxes that we look at. We also look at differential fluxes. I'm not going to talk about the details of the difference, but just know with integral fluxes, it's a threshold that you reach, 10 MeV and higher. Any particle that's higher energy than that fits into this bin. 50 MeV and higher. Anything that's 50 MeV and higher than that fits in this bin, that type of thing. Differential fluxes say, oh, between 20 and 30, just what's in that little window, between 50 and 100, just what's in that window. Differential fluxes look at a small window of energies, whereas integral fluxes look at a threshold and above. Okay, anything lower than that, it doesn't count, but anything higher than that does. So there's a different way of looking at fluxes and for different reasons. These are integral fluxes, so that's just a threshold and anything above. Okay, so in this case, when we look at integral fluxes from GOES, okay, this is how the Space Weather Prediction Center labels it. There are two thresholds. One is for the 10 MeV channel and one is for the 100 MeV channel. And anytime the 10 MeV channel, just like they say right here, anytime the 10 MeV channel, they're saying proton E, meaning proton energy, okay? It's the 10 MeV channel is, and they say the greater than 10 MeV channel, that's the integral flux part. Anytime it's greater than 10 PFU, proton flux units or above, that is a threshold for a radiation storm, Okay, so this blue line, this blue dashed line is at 10. That's 10 proton flux units. And anytime the radiation for the 10 MeV channel, the blue channel, goes above that threshold right there, okay, so right here, right, that is a radiation storm, okay? Now, there's another classification. It's for the 100 MeV channel. Anytime the greater than 100 MeV or 100 or greater MeV channel goes above the 1 proton flux unit, it's also considered a radiation storm. So here's the green line is showing the 1 proton flux unit level, okay? And look, that green 100 MeV channel never reaches it, does it? So this is a radiation storm for the 10 MeV protons, not for the 100 MeV protons. But SWPC doesn't care. Either way, this would be classified as an S1 radiation level. But there are times, because the two channels don't always pay attention to each other. The two channels don't always act right. Sometimes you get a proton radiation storm where the 100 MeV channel is huge. And it doesn't necessarily peak above the 10 MeV channel, but it gets really close to it. That's what we call a hard spectrum. And it triggers a radiation storm because the 100 MeV fluxes go above 1 PFU. But the 10 MeV channel may not have peaked above its threshold, which is 10 PFU. So either or of these triggers will cause us to say it's a radiation storm. Okay? So we pay attention. That's why we pay attention to all these different energies, is because it's either or. And like I said, you know, we fool ourselves into thinking something isn't a radiation storm or isn't going to be dangerous if we only looked at one channel. Okay, so without belaboring that point, let's take a look at something. I'm sure all of you guys remember the Carrington event back in July 2012. There was so much noise about that, saying, oh, if this event had just been launched 8 days sooner, we would have hit a Carrington class event. Well, yeah, this is that one. In July of the 24th of 2012, this is the Enlil spiral. You now know, you guys are now experts with Enlil. We're looking down at the sun in the center. These are spiral arms. And you know the dashed lines are actually magnetic field lines showing where the magnetic field connectivity to the sun is. And anybody who's seen the CME talks or the CME mini courses know when that thing launches, that's that big CME that launches out. Look how fast that thing is, okay, coming out. And look how massive it is. Look how far, how much extent, how big of an extent it has, right? Just the CME itself is 180 degrees. And look how fast it drives out within like not even 2 days, okay? When we look at that radiation storm, now let me go back because I want you to look at where stereo A, stereo B, and GOES is, okay? So on this plot, stereo A is this square, because this is 2012, so stereo A is this guy. The CME goes right over this pi, right there, boom, okay? Stereo B is the blue square down here. I can point to it, okay? See where it is relative to stereo A? And then GOES, the GOES spacecraft is clear at Earth, okay, over here. So between those three spacecraft, we've almost got the entire solar system, you know, all the 360-degree view around the sun, right? So at stereo A, remember that's the one that got slammed by it. This was the view. Okay, it's right at the beginning of the flare. That's the flare occurring. And I wish I'd do a movie of this, but it's a beautiful movie if you actually ever see it. I can show it to you sometime. And you just see this massive dimming, this massive coronal mass ejection, this massive flare, and then the radiation storm comes pretty fast. So here's stereo A. If I look at this here once again, here are a bunch of lines, right? We've got, once again, 23 of July, 24 of July. And here's the proton flux units going up, so intensity going up. And if you look at the black trace, this is the low energy protons, relativistically speaking, up to 12 MeV, okay? And you can see them rise as that flare hits, and then you can see them go up, 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 up. and then that shock passes. We go up, 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 up in the black line. Right here, here's the shock. Whoosh, look at the big ESP. A lot of energetic storm particles in this puppy, okay? And that is stereo A, the low energy stuff. The blue line is same thing, stereo A, right? And it's higher energy stuff. This is up to 100 MeV. And again, the particles go up. Look how close, this is a much harder spectrum. Look how close the black, the low energy stuff, and the high energy stuff is. Look how close the fluxes are. Okay, this is an example of where you would have a radiation storm definitely in the 100 MeV stuff, much faster than you would in the low 10 MeV stuff, okay, because the spectrum is much harder in this sense. So then the particles rise, 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 and again, the energetic storm particles, okay, with the blue. Now, that's stereo A. We expect that. You know, it's not a super well-connected thing, even though the thing is coming, you know, because stereo gets slammed right by that CME. It's not as well connected as it should be, but it's connected well enough. Now, remember stereo B. Stereo B is down here in the red and the yellow. Now, it's not connected well at all. Stereo B, relative to it, as it looked at the Earth, the CME was going off to the east. So it's really poorly connected, right? Very poorly connected. And you can tell that. Look how slow the rise in both the red and the yellow channels are. They rise very, very slowly. Okay, as a matter of fact, it takes more than a day compared to where stereo A is for those particles to rise, because they're having to go and travel across the field, doing cross-field diffusion against that Archimedean spiral to get to stereo B, but they still get there. Okay, that's how big this thing is. And now look at the green line. Do you see this green line? Notice that it rises almost as fast as it does at stereo A. You know what the green line is? That's GOES. That's Earth. That's Earth. Are you kidding me? We got a reasonable radiation storm at Earth as well as at stereo A and stereo B. So the red one you'd expect, right? The red one here. Stereo A, absolutely you expect to get a radiation storm. Stereo B, a bit harder, right? Because it's east, but reasonably close. But Earth? Holy merd. Earth over here. It's a western connect, but it's even further away. So you're almost talking about 270 degrees across the solar system. You're getting a radiation storm. So it's almost like the sun could have launched this puppy, a Carrington-class event, anywhere. And anywhere, even on the backside of the sun, where Earth was, we didn't even see the CME. We didn't even see it. We didn't even know it was launched until stereo A, showed us. We saw maybe a chronograph of this thing blowing out, sure, but we didn't see the source region. This thing was behind the west limb of the sun, way behind the west limb of the sun, and we still got nailed by this thing. That's how intense radiation storms can get. You cannot see the flare, you cannot see the CME, and yet you still get the radiation storm. Radiation storms are probably the most enveloping, the most intense thing, if you had to talk about space weather, probably the most intense thing when it comes to that, because they're both driven by flares and CMEs, and they can spread out in longitude so dramatically. And of course, when you think about that at Mars, what that means is that if you get these really big events, it doesn't matter where they're launched, they'll be seen. They'll hit. The chances of them hitting a planet or a spacecraft or something, a colony, a Mars colony, for example, is large. It's a big deal. And we've had this, right? We've had Curiosity. I mean, we've had to shut down Curiosity multiple times. Curiosity has been so great, they actually have a Twitter feed that even talks about it. Here's an example back in 2013. Curiosity even tweeted about how it was shutting down. And we've had to do this multiple times with it when it comes to this, with all of the rovers. Now, Curiosity is the first one that actually had a radiation monitor that actually detected the radiation, because we're trying to think about, okay, we want to land people on Mars, how are we going to do it? What type of environment are they going to deal with? And what we've learned is that it ain't the Martian. It's not going to be Matt Damon hiding behind his little potatoes. People are going to have to dive underground to survive these radiation storms without getting sick. And the idea of long-term colonies and people, you know, settling on Mars and living out their final days on Mars is just such a far-fetched idea. It's almost ludicrous. We don't even know how plants are going to be able to grow and handle the radiation environment that will be on Mars, let alone people. So, you know, we've got a lot of things that we worry about. And here's another example. This is much more close to home and much more recent. Anybody remember Harvey and Irma back in 2017? Right, I've talked about this particular event before. This was region 27 or 2673. That was this really ugly region on the sun that grew very, very quickly. This is what we call a bad actor. And what you're looking at are magnetograms, and I'm not going to go into the details of this because I have in the past. But suffice to say, if red and blue touch each other in these types of diagrams, that's bad. And here we have multiple bands of red and blue touching each other. It goes like red, blue, red, blue, red. By the time it gets to this over here, you can see multiple bands. And it was just a recipe for disaster. And unfortunately, that was happening when Irma was barreling down on Puerto Rico and just decimating Puerto Rico. We had radiation storms, we had solar storms, we had geomagnetic storms. I mean, I can't even tell you how many. We had 4 X-class flares, we had like 25 M-class flares, 2 radiation storms, 2 geomagnetic storms. I mean, you know, this is the thing about bad actors, is that when they get mad, they rotate onto the Earth-facing disk, or they emerge, and they're angry, and they just fire storm after storm after flare, just all the way the whole time that they're rotating across the Earth-facing disk. And this one, of course, had to launch a flare where? Where did it have to launch the second largest flare of the solar cycle, an X8.2? On the west limb. Do you think us forecasters were happy about that? No. As a matter of fact, this flare was probably larger. It probably was the largest flare of the solar cycle. The reason why it only registered as an X8.2 was because this flare actually occurred after the sunspot had rotated out of view. This sunspot, this flare, was occulted, what we call occulted, meaning it was partially blocked by the sun itself. Okay? So we only saw part of it. When this launched, not only did it launch a very prompt, as you can see, radiation storm, right here. Look how fast those energies went up, right? Really good connectivity, okay? But really pretty hard spectrum too, because we had the green is the high energy stuff, the red is the low energy stuff, and those traces are pretty close together. So really high energies. S3 level storm. But let me just compare it. Here is the well-known Carrington class event on July that we already looked at, right? Okay, that's the one we talked about where we're basically 360 degrees around the sun. We saw radiation storm. Look at this guy. This is the Carrington class, or near Carrington class event, what I call the suspected Carrington class event of 2017. That was the one where that X-flare launched. Look, I'm going to stand out of the way. Look how close in size and in speed, just from the predictions. Can hardly tell them apart. Now, guaranteed, the Carrington class event, this side, is a little bit faster. Maybe a tiny bit bigger, definitely a little bit faster. This guy's not quite so fast, so maybe borderline Carrington. We didn't have a spacecraft that, unlike Stereo A going through this one, right through the middle, this one, Stereo B, went through, but the problem is Stereo B was dead. So we don't have any actual in situ measurements of this one. We don't really know how big this guy was and how fast it was truly going. Believe it or not, this event clipped us. See how it's showing how it's close to clipping Earth right here? The storm itself clipped Earth. Now this thing was launched. If I had a gun, I would actually be pointing. If you're Earth, I'm actually pointing the gun away from you. That's how the thing fired. And imagine having a gun where you're pointing the gun away from you, you know, and the bullet is so wide that it still hits you. And that's what happened. We actually got a G1 level storm from this guy. Imagine if we had been in the center of it instead of at the edge. Whew. We got lucky. Now, again, I just have this up to show kind of the, well, I think I flip it over. Yeah. I just have that now. This is now actually I can stand on this side. I just have this aligned to kind of show you where the Archimedean spiral is and where the CME is, get out of the way, relative to this event. So you see that event going out, you kind of see, and you can see here with this diagram now, this solar slinky, kind of this yellow bit is the similar thing as that thing coming out of the sun. So you can imagine that diagram with all the Archimedean spiral arms coming out and where things are really well connected and stuff like that, right? And if I recall, Mars, see where Mars is? Can you see where Mars is? Right there. Over, over, over. There, that's Mars. Okay? Curiosity, right? Beautiful. Where's that on this diagram? Oh, the really well-connected part of the Archimedean spiral. Oh yeah. Think they got a radiation storm? Think they got a big radiation storm? The radiation levels for this event at Curiosity doubled and remained high for nearly 2 days. This is the Southwest Research Institute PI for Curiosity's rad detector. This is the largest event we have seen since Curiosity landed in 2012. Okay? The ground level event here was so intense that they haven't, even the events, even that other event where Mars actually saw it, the Carrington class event, wasn't nearly as big as this. And all the other radiation events that they had during that solar maximum wasn't as big as this. It just so happened that Mars happened to be at the right place to get the prompt and very intense, the really good connectivity that can cause real serious issues for radiation storms. If this had been a real human, okay, they would have been sick if they had been on the surface of the planet. Who knows how sick they'd be? I'm sure that these types of things are coming out. I haven't looked for a human equivalent to this yet, but this is informing NASA and all the scientists and medical people who are working on Mars colonization. That's why we had this rad detector on Curiosity. But what we've found is that the intensity of radiation is much more than we thought it would be on Mars. The problem is, events like this, you've got 15 minutes, 20 minutes, maybe an hour to get everybody safe, stow your rovers, get in your underground bunkers, and hunker down. Okay? We need to be very, very careful. And here's my last couple slides, just to give you an idea of radiation storms at Earth. This is SOHO. This is the solar array on SOHO. SOHO is sitting outside of the Earth shield, out in front, pristine interplanetary field and solar wind, just the pristine solar wind. Not dealing with radiation belts, not dealing with any complications of that, because that's a whole nother story, trapped radiation. What you're looking at is time coming on this side, or across this way, and then this is essentially the percent functionality, I guess I should say, of how well the solar array is performing. Okay? Notice that the solar array begins to degrade. Tick, 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 tick. But there are certain events over time in particular that take a huge bite out of its efficiency. Now this is because these are solar radiation storms. Every single one that they've got pointing are big solar radiation storms, time and time and time again. This is because energetic particles, not only do they degrade the cell with radiation dose, but they also darken oftentimes the coating. And I don't really know what coating is on the solar array on SOHO, but there are coatings that we put on solar arrays to keep them from charging up a lot of time. And it oftentimes darkens the glass. It darkens these coatings and makes it like we have sunglasses on our solar arrays. So radiation storms can cause a lot of havoc. Not only can they do damage to either temporary or permanent damage to CCDs. SXI is a classic example where we actually get permanent damage from X-ray and radiation storm stuff. But you also do damage to things like solar arrays. So the health and safety of these spacecraft are really impacted by radiation storms. Now, not only that, but we also have single event effects. For those of you who are familiar with electronics, there's all sorts of things that we call SEEs, single event effects. These are things where particles will hit typically intelligent electronics. Either it's memory or it's the brain, the computer brain, ASICs and FPGAs. There's all sorts of names for these things. But the particles will hit these and it will flip a bit. It will change something, or it will deposit energy, deposit a charge, or it will deposit itself if it stops in the material. Change the voltage, change the bias, change all sorts of things, change junctions. There's all sorts of complicated things that it can do to change how that semiconductor works and functions. And that can be misread by either the brain, the intelligence of the electronics, or just it causes that particular part of the electronic not to function very well at all. We have things like latch-ups and burnouts and all sorts of things. So single event upsets, that's a way of talking about something that actually disrupts the function of something. Single event upsets can be recoverable, as they are typically with like memory. You get a memory glitch, you reset the memory, you're good. Or it can actually cause major issues. Single event upsets can cause a latch up or a burnout where it latches something into a mode that you can't get out of it. Resetting it doesn't matter. And sometimes it can set a short to cause a thing to heat up, and it literally will burn out till it's gone. You can get spurious commands. Can you imagine having a single bit flip that commands then the spacecraft to turn its thrusters on and it goes off? Yes, we have seen this before. These things happen or cause the spacecraft to rotate. They get these commands that actually activate the spacecraft, thinking it's getting a command from the ground to go do something in particular. So there's all sorts of both resolvable and unresolvable single event effects that are caused by these really energetic particles. And here's an example. This one is the single event upsets, the SSR single rates. I don't know, single rates maybe. I don't know if this is memory. Probably is high energy. No, it's not. It's not talking about what it is, but a lot of these are memory bit flips and things like that. But you can see. I don't even know what this is. This reading? I don't see a label, so I don't know what it's reading. But it might be a voltage or a potential or something like that. But you're seeing these singles. You're seeing these little glitches. See it? And these are particle storms that are coming in, and they're all labeled because we actually have found specific space weather radiation storm events that have caused these types of problems. And so we have to deal with these all the time. This is one of the reasons why satellite operators hate radiation storms. And it gets even worse inside, this is outside of Earth's magnetosphere, but inside Earth's magnetosphere we have to deal with those things, plus cosmic rays, plus the trapped radiation from the radiation belts. So it's even worse inside the Earth's magnetic shield than even outside it, sadly enough. And single event effects become a real issue, especially at low Earth orbit, because of what we call the inner belt, the radiation belt, the one that's closest to Earth, actually has a lot of protons, a lot of particles that are very, very energetic, and can cause all sorts of upsets. But we've seen this many times in spacecraft, and the idea that this kind of stuff is only what we have to worry about inside Earth's shield. Well, here's SOHO sitting outside of Earth's shield. If we go to a trip to Mars, we're going to be dealing with this stuff. We're going to be dealing with bit flips. We're going to be dealing with solar array degradation. We're going to be dealing with all of this stuff. And that's just on the way traveling there and back, right? Once we get to Mars, the astronauts themselves will also still be dealing with the particles because they come all the way to the ground. It's not like here on Earth where you get a respite. You stand on the ground, you're safe. No. At Mars, you're going to be dealing with it all the way, the entire time you're out there. So we have a lot of work yet to do when it comes to making space and space travel safe. And I'm hoping we're going to learn a lot from our moon, our colonization on the moon, to be able to then transfer that information, that knowledge to Mars. But getting to Mars is only half the battle, and I think a lot of people right now are super excited about getting to Mars because we have this window that I guess up to 2032 or something, Mars is its closest approach to Earth, and so it shortens the trip from Earth to Mars and back again. And everybody's like, good, so we have to get it done in this window, because then it's going to be another, I don't know, 20 or 30 years before we do it again, before we get that opportunity again. But it forces people, it ends up getting people to mistakenly believe that it's all about the travel. It's all about the interplanetary travel. And then once we land on Mars, whew, we're safe. And that's just not the case with Mars, because its atmosphere is so tenuous. And that's a real issue. And I don't think enough people realize that space weather on Mars is literally all the way to the surface. It's not just what's up in orbit. And, space weather is Mars weather, period. So there's a lot of other things, and it also has to do with radio communications and stuff like that, because the space weather, the radiation storms affect, Mars all the way to the surface. So radio communications is going to be wiped out, even on the surface. Even direct wave communication, direct ground wave communication will likely be wiped out on Mars during a radiation storm. It's going to be like a blackout all the time when there's these storms. And those blackouts can last, as you've seen, they can last a day or more, maybe several days as a CME passes over. Actually, at Mars, it's going to take longer, because Mars is further out than Earth. So you could have a radiation storm that at Mars will last 4 or 5 days easily. Could you imagine not having any radio communications for 4 or 5 days? It's insane. So there's so many issues that we have to deal with, especially with radiation storms. The biological aspect, the radio communications aspect, the electronics aspect. There's just so much we have to deal with, and we just aren't taking it as seriously as we need to. So, I'm all for Elon Musk, pushing on, but I also don't want to lose lives unnecessarily. So hopefully we can raise the awareness of radiation storms and what they mean before we get too ahead of ourselves. So, and that's all I have for today, guys. I'm gonna, like I said, I'll go over some of this the next time for those who dropped off earlier. But thanks for sticking with me. And if there are any questions, I would be very happy to take them now, since I've been on for 3 hours, it looks like. And let's see, anything. Oh yes, poor Stereo B. My goodness. Yeah, Stereo B is a sad story. We think one of its gyros failed, which means that even if we were to try to get it back online and heat up its hydrazine, we probably couldn't get it stabilized. So I'm not sure. I'm not sure we're ever going to hear from Stereo B again. The one attempt at one time we actually did light it up, and it communicated with us. We couldn't even keep it online for very long, and we just don't know if it's tumbling out of control or what it is, but it's just not able to charge its batteries enough. And when we try to heat up the hydrazine, I think it just killed the batteries again. So I don't know. I don't know if we'll ever see Stereo B again. It's really sad. But was there an event today? I don't know. That's a good question. Not that I saw. We had I'll minimize this. We had we had active conditions for a little while. It was just kind of not really a lot going on there. I'll show you my favorite website. That's SolarHam. Oh, and anybody realize that we've got a new spacecraft for X-ray flux? Oh yeah, look at that. We had a little B-class flare. Oh, good. Yay! We had a B-class flare. Oh, how cute. Look at that. Son of a gun. Let me see if I can stand on the right side here. See right here? Yeah. We're waking up, maybe. A B 1.4, it looks like. Yep. Isn't that good? Right when we were talking, too. Nice. So, actually, well, no, a little bit earlier than that. So, I'm sure it's from our new region. Well, I won't dig into that too much. We've already been on for so long. But yes, I'm sure it's from our new region. And I am working on a new solar storm forecast. I just hadn't gotten it done because I wanted to do this class today. But look for it in the next day or two. Probably tomorrow I'll have it out. And I'll definitely be talking about this event. We're close, guys. We're so close to starting solar cycle 25. We're really getting close. It's good to see flares in the northern hemisphere because the northern hemisphere has been the one that's been lagging. So once the northern hemisphere and the southern hemisphere both say we're green to go for solar cycle 25, then you'll see activity rise real fast. But we're definitely beginning to get there. So what's your thoughts on planetary alignments governing sun cycles? Oh, the problem is, like I've mentioned before, the internal forcing with the solar dynamo. There's so many different layers that we're beginning to learn, that there's different convection patterns, and they're all magnetic, and they're all kind of helping figure out what the dynamo is. Once we understand those internal processes, then we'll be able to better, because then we can isolate and get a model that actually works with these. Then we can isolate what those effects are and add in the forcing, the planetary forcings. Do I believe the planetary forcings happen? Yes, absolutely. Do I think it modifies and creates an envelope of the internal dynamo and the activity of the dynamo? Yes, most likely. How big of an effect is it? I don't know. And I don't think anybody can say that with any real confidence, because there's scientists on both sides saying, well, it's just not, we've already checked the forces and we know what the gravitational pull is, and it's just not enough to overcome the plasma flows and the forcing, the internal forcing, so we don't think it has much of an effect at all. And then there's other people saying, no, it does, it's just enough, and it's a little bit more than enough, and in fact it might modify this flow that way, and just, so there's people on both sides of the spectrum that are arguing back and forth. And again, it's all speculation, even though it's educated speculation by a bunch of people who know what they're doing. It's still speculation until we get models that are robust enough for us to subtract out the internal effects so that we can then see what's left. Once we can see what's left, then we'll have a better idea of how much of an effect it has. But quantitatively, we're nowhere close to determining that. But do I think it has an effect? Sure, absolutely. They always do. They always seem to have. Tides are important. Tides are important, very important to our planet too. So, okay, do it again tomorrow. Yeah, right. You hear my voice? No, I can't. But what's neat is that the Millersville crew now, the class I'm teaching in Millersville is now ahead of you. So you're no longer the guinea pigs. The Millersville students are. So the next course I teach will actually have been taught at Millersville prior to being taught to you. So hopefully I'll be a little bit smoother. Unfortunately, that also means I'll probably add more detail and could slow us down a little. But I think all of you guys are enjoying these courses. So it's all fun. I'm enjoying it all. But no, only one a month for you guys, because these are long classes. These are 3-hour classes. So it takes a lot out of me. Do other stars act in the same way in regard to radiation, solar storms, etc.? Or are different star types acting differently? Are they too far away to tell? I'll barely answer this question because it's really getting a far field. I am not an astrophysicist. I'm not an astronomer. So I have to be very careful, so I'll put a disclaimer right out in front and say this is not my field of expertise. But I have learned enough about these areas of study to know that, yes, there are solar flares and there are coronal mass ejections. We have detected them in one fashion or another. Not nearly like obviously we detect them on our own star, and the ones that we have detected have been massive, because they have to be. These stars are so far away that it's really hard to tell really what's going on. But we just know that these events that we're detecting in other stars are very similar. They are space weather, as the classic definition. But we're detecting far more in the way of like radio bursts. We're detecting far more in the way of like solar flares, because we can see the lights, the X-ray, intensities and things like that change. I don't think we've actually ever done anything even close to a remote detection of a coronal mass ejection, but we can imagine that they're being launched. So yes, some of these stars are acting the same way our star is. It's just that a lot of these stars are far more intense in their space weather. They would be literally planet eaters. Their space weather, the CME, would be just so intense that it would cook anything that it came through. And we really are limited to detecting really intense space weather just because of the limited sensitivity of our instrumentation and the fact that these stars that we're detecting space weather on are so far away. Do they have space weather like our star, or are there other stars that have mild space weather like our star does? Probably. I wouldn't think that our star I mean, our star is a very common star. It's 1 out of every 15 stars is like ours. So yes, I'm sure there is space weather very similar to our star coming out of other stars. We just don't really have an ability to detect the quieter stuff. Not like we have the ability to detect the really crazy stuff, which is what astronomers love to talk about anyway, right? They want to scare the bejesus out of you with how dangerous the universe is. So I try to do the opposite. I try to show you, oh, these are big, but they're manageable if we're savvy. So I try to rein it in rather than blow your mind too much. I try to blow your mind in a good way, not a scary way. So hopefully that answers that question. Don't have the technology to get us there, according to NASA. Well, yeah. There are a lot of really difficult problems, and space flight is not without risk, and there are always going to be some inherent risks, and the early pioneers of it are going to be more at risk than others. And as long as they know the risks going in, that maybe they not just won't come back because the spacecraft doesn't make it back, but they may be cooked along the way. If they're willing to take those risks and die maybe a really nasty death, there's always going to be people who are willing to do that. So I think there's always going to be that spirit of adventure, and we'll always push forward. I just want to make sure that that you and me, that the average person knows that space is hard. It's not like it is in the movies. It's not what Hollywood depicts it as. And a lot of the things that Hollywood makes us scared about in the movies really isn't the main fear. In some cases, it's not even anything. And areas that Hollywood has completely neglected are actually the real issues. And I can't tell you how many Hollywood stories could be written about space weather that would be really cool. That'd be major blockbusters. But nobody's willing to write them, probably because they don't even know that it's possible. Stanley Kubrick and all sorts of others have defined space a certain way, and you've either got to, space is dark and doom and gloom, and you got to go crazy. You have to have at least one token person who goes nuts, right? I mean, every good space flick has some psychological, bent to it that where somebody has to lose their mind, or they have to have a mutiny on a ship, and then that person loses their mind and kills their captain. And I mean, it has to be something crazy like that, right? Or there has to be rocks raining from space down on Earth, or ripping spacecraft apart, or something like that. God forbid there might actually just be, a CME, for goodness sake. Or it has to be the sun dying out, right? The sun has to be dying, and we're going to fly into a sunspot to reignite the sun, right? Or a coronal hole, right? Because it's a hole right in the sun. I mean, the sun is splitting apart, and we could fly right into the center of it and reignite it with a nuclear weapon. It's just, wow. I mean, it's just crazy. Any of you guys ever take my Millersville side, my Millersville courses? There's a side of the course that I'm teaching that's called astrosociology, and I talk about how we've been socialized into believing certain things about space and what space weather is and what space weather isn't. And it's become a really fun part of the course, because we're breaking down all of these biases that we don't even realize we have, that Hollywood has helped put us there, or put inside us, and we just kind of carry it on over time, and we don't even realize that we have these things. And so with Elon Musk and SpaceX and everything else, and going to Mars and the Martian and all this kind of stuff, we have all these expectations, and there are so many of them that have been perpetuated through Hollywood and now in through the commercial space race, that really are, some of them are stupid and silly, and others are very dangerous. And so we need to try to break down those things and rebuild ourselves with a much healthier understanding of space and space weather. So I'm trying to do that in these classes. So, okay, anything. You sound like you could write it. Oh, write a story like that? I probably could. Yeah. If I have. Unfortunately, that's down on the priority list. I do want to write something like that, but I want to write it more like Carl Sagan's Cosmos. I want to write the space weather version of Cosmos. I think that that's a much more important thing, much more critical thing to do, and really kind of talk about some of these astrosociology issues, because it's if I could get us all to understand how pop culture has really framed our understanding of what space weather is, and how we need really to make a paradigm shift into a much more realistic view of things. I think it would really be very empowering and very exciting. And so that's really much higher on my list than to just write a sci-fi movie, although that would be fun too. So thanks for that question. That was cool. You'd like to learn astrology or astrosociology? I don't really do astrology. I mean, I like astrology. I think astrology is fascinating. I think astrology is picking into the universe's cosmic clock, how it assigns personalities with different zodiac signs and the cosmic movement of things. I think it's very fascinating, very fun. So yeah, so unlike Carl Sagan, I don't rip on astrology, not at all. I think it's very fun. I think there's room for it all. Not a Grand Slam minimum that I'm worried about. I'm more worried about the magnetic polar shift. Oh, Earth shift? Don't. Earth will flip, yeah, but it's not the whole magnetic field of Earth that's flipping. It's only the dipole component. It will be a very fascinating time to live when the dipole field disappears and what we're left with are the higher order moments, meaning the quadrupole, the octopole, and higher order. Yes, the field will be weaker, but now instead of a north pole and a south pole, we'll have 4 poles. That's what the quadrupole means. So we'll have a northeast and a northwest and a southeast and a southwest pole. We might have aurora in Hawaii. We might have aurora in Chicago. There'll be aurora in Singapore all the time. It'll change space weather dramatically, at least its effects here at Earth. And I don't even know if we'll have radiation belts, because everything is going to be so disorganized in near-Earth space that I don't even know if radiation belts will be able to form. It's going to fundamentally, we'll have to relearn space weather all over again. But it's not going to strip off our atmosphere. It's not going to be a problem. Even Mars doesn't have a magnetic shield at all, and we're talking about colonizing it. So don't worry about Earth's magnetic field flipping or even disappearing for a short while. Mars hasn't had one for millions of years, and it's still okay. Its atmosphere is real thin, granted, but it's taken a long time to get there. Earth's magnetic field is just simply flipping. Okay, so maybe bits of the ocean are going to evaporate a little bit more, but is it even going to be measurable? Probably not. The cool thing is where aurora is going to be and how our compasses are going to work. Our compasses are going to be so messed up. We'll have a compass that has 4 poles. Oh, it'd be crazy. GPS is going to go nuts. It'll be fun. But that's probably not going to happen for a few hundred years, so you're going to have to deal with, stories from your great-grandchildren are going to be able to tell, not us, unfortunately. But don't worry about it. It's not going to be the end of life on Earth. Not at all. It's more, look forward to it as something more fun than anything. Yeah, not happening in our lifetime, right? Yes, read Cosmos and Psyche. Astrology is real. Mars effect. Yeah, there's all sorts of neat effects and things to read about in astrology, and some fun stuff to speculate in. It'd be neat if we ever got to a point where we understood, the forces, all the electromagnetic forces and gravity and stuff like that well enough to be able to even talk about stuff. I mean, think about it. We didn't even know what dark matter was not that long ago. In the 1950s, we didn't even know we had a solar wind. So imagine if we were ever able to figure out how nature works so well that suddenly astrology actually fit in scientifically and mathematically into our universe. I think it'd be fantastic if it did. I have no idea how, but that's because we have 21st century science. I mean, that's just where we are right now. But I think it's cavalier to just dismiss stuff like that simply because we don't understand how it works. It's lasted too long, and there's been too many people that have really gotten something good out of it for us to say, okay, it obviously is false. Well, why? If it was false, it would disappear. Nobody would find it useful. The fact that it's lingered for so long and people have found it to be useful shows that it's robust enough to survive. Therefore, there must be something to it, right? Anyway, okay. So, are we done? Have I tired you all out? Whew, it's getting harder and harder. I used to be able to do it in 2 hours and you guys would all be out of questions and done. Now it's more than 3. You guys are really getting some more stamina, too much stamina. You're much better at this than I am. So, okay, hopefully I've answered all your questions. I'm going to check Patreon real fast to see if there's anybody having any questions there. And if not, then I will say good afternoon. Let's see, I'm reloading. Anybody have any questions? No, good. Okay, everybody's good. Oh, okay. Single event effects, a danger for life support systems on Mars. Sure, absolutely. Absolutely. We're going to have to solve all these problems. Next time I'll show you a slide where even medical supply companies, just for terrestrial flights, people who have IEDs, who have pacemakers, they have soft resets sometimes, just flying on terrestrial planes. There are medical companies now who are looking into radiation-hard electronics for their pacemakers so that their patients can fly without worrying about, having their pacemaker reset. Could you imagine? I mean, it's just crazy. This stuff is, as space weather becomes more mainstream, we're going to see more and more stuff like this with the medical fields. The medical field and space weather fields are going to come together. And I think we're going to see that the fastest in aviation when it comes to radiation storms and things like that, both for astronauts and aurora tourisms, space tourists, as well as people who are doing asteroid mining and working in near-Earth space. We're going to have a lot more humans out there. Plus, just airline flights. I think radiation storms are going to be one of the big, fastest growing areas of space weather, medical and space weather research. So, science and stamina go together. Yes, in Tamitha Scove's world. Very cool. Thank you. It's sweet. I appreciate that. Oh, good. For you amateur radio operators, 20 meters has improved. That's good. Check. I have no idea. 341. I'm not answering that. I don't know who that is. Doesn't look like anybody I know. So, okay. Any other questions? Let's see. I think there's galactic waves, even larger scale, that are affecting things possibly. Don't know. Again, that's getting into astrophysics and cosmology. That's way out of my field. I'm much more into our solar system. Just making sure no one's texted me that anything's wrong. Okay, I'm good. Okay, time to rest, Tamitha. Yes, Jerry, thank you. I know. I need to close this down. Thanks, guys. I appreciate this. No rest for Tamitha. You guys have been wonderful today. Thanks for hanging in there with me. And I hope this has been a nice distraction for this afternoon. A little bit of, normalcy in a crazy, crazy world right now. So enjoy, and next time we will go into cosmic rays and a lot of the fun there. I might even talk a little bit about trapped radiation. It all depends what you guys want, okay? So take care till then, and I will be talking to you soon.